Okay. So in our last session, we spoke about how SVM tries to solve the classification problems. So what it actually tries to do is it tries to find out the support vectors. What are the support vectors? Support vectors are the boundary points of the clusters, right? So if these two are called as support vectors. And if it is trying to find out a hyperplane in between these two support vectors, and the distance from the hyperplane to each support vector is called as margin. So if the margin contains, or if SVM allows misclassification, that is called as soft margin uh, SVM. So if it is not allowing, you know, misclassifications, then that is called as hard margin SVM, right? So in soft margin, it actually allows misclassification of the data points. So if you see this case, this red dot belonging to a particular cluster or a particular class is an outlier. So if you consider this as a support vector, we are going to get, the hyperplane here, because hyperplane is always will be in between the support vectors, or the um, what we call it as we the boundaries of, or the edges of the cluster, right? So the boundary will always be in between them. So but this, if you consider the outliers, what happens is hard margin classifier will be more sensitive to the outliers, right? It is super sensitive to outliers. That is the reason, even if you have a test data coming up, what happens, the test data, if the test data is coming here somewhere, something like yeah, if the test data is coming here, where is that, if test data comes here, what happens, that as if the test data comes here, it classifies that as green, that particular dot belongs to green cluster, right? But that is not, I mean, this is close to green cluster, but it classifies that as red cluster. So that is the problem with um, hard margin SVMs. So soft margin SVM, what it does, it ignores, it allows misclassification. So this point is considered is misclassified, and it is taking these two, right? These 2 points as support vectors, and it tried to find out the margin in between these two things. So such kind of classifiers are called as soft margin classifiers, or if it in case of SVM, we call that as soft margin SVM. So that is what maximum marginal classifiers are: hard margin classifiers and soft margin classifiers. Now, how far do we need to? So this is where we actually discussed, right? So how far is considered? How many misclassifications are considered as good amount of misclassifications, right? So in this case, we allowed only one misclassification. So the margin is coming here. So in this case, we allowed so many points as misclassifications, right? So we allowed so many points to be within the margin. So what is the criteria for that? How do we determine the location of the threshold, right? So that is what we're going to study today about the soft margin classifiers, and also deriving the objects. So what is the main criteria of support vector classifiers is that it has to find out, it has to maximize the margin, right? We wrote the objective as well. What is the objective we have written? Soft margin SVMs tries to maximize the margin. Okay, that is what the objective is, what we have written, and we have some constraints as well, and that we are going to see today. Okay, so now we also have talked about some mathematics related to basic math related to soft margin SVMs, and in that we have actually found out this formula, right? So what is the formula of a point from the hyperplane, the distance of a point from the hyperplane? So if this is the two-dimensional space that we do have, and we will have two, let's suppose these are the support vector classifiers, and this is the line intercepting the support vectors, or the line passing through the support vectors. Okay, and then once we found out these two support vectors, the hyperplane is the distance. I mean, the hyperplane is a point in between these two support vectors, right? So hyperplane exactly lies in between these two lines. So this is the hyperplane, and these two are the support vectors. We can have a number of points above that hyperplane. That means the other points, like this is the support vector. The two closest points of different clusters will be considered as support vectors, and the other points. Okay, so you can have other points beyond this line. We will have other points. So this is like, if you consider these points are linearly separable. Okay, we will talk about non-linearly separable cases little in a little while, but let's derive this objective. So I'm saying this is the objective, and how this objective is derived is something that we have to find out. So this hyperplane is written as W transpose x plus b is equal to 0, right? That is the equation of the hyperplane, which is h of x. Now, if this is the, we are trying to maximize the margin, right? So we call this as margin, right? The distance from the hyperplane to the support vector, the line intercepting the support vector, is called as margin. This is also the distance of the margin. So these two are always equal because the hyperplane will always be in between these two lines, or the line, what are these two lines? These two lines are the lines intercepting the support vectors, right? So these two distances are equal. So this is called as margin. Now we are trying to maximize the margin. So now when you say trying to maximize the margin, you're trying to maximize this distance, right? Okay. So how do we calculate the distance of this of a point R? Let's suppose this is the support vector, and this support vector, let's mark this as point X. Okay. Let's mark this as point X, and this is, and let's call this distance as R. Okay. And now what is R? We calculated the R, right, in our last lecture. What is that? H of X by mod W. That is the equation that we have derived, right? How we have derived this? So we found out something like this. So this is the hyperplane, and this is the point X, and this is the projection of the point XP, and this distance is R, and this is the XP vector, and this is X vector. And we found out that XP plus R is equal to X. And now we know h of x is equal to, what is h of x? H of x can be written as W transpose x plus b, right? Now h of xp plus r is equal to W transpose xp plus r plus b. I'm just replacing x with xp plus r because x is equal to xp plus r in this case. And our whole criteria is to find out this r, right? So this can be break down to W transpose xp plus W transpose r plus b. Okay. So now if you take this, I'm keeping these two terms at one place. So this becomes W transpose xp plus b plus W transpose r. So W transpose xp plus b can be written as h of xp, right? H of xp plus W transpose R. H of xp is will goes to 0 because xp is a point, the projection point of x on hyperplane. So any point that lies on the hyperplane is equal to 0. So this is equal to 0. Now we remind with this one, right? Now we remind with what? Um, h of x. This is h of x, right? H of x. xp plus r is nothing but h of x. So we remind with this. H of x is equal to W transpose R. So R can be written as H of x by W transpose is nothing but the modulus of W, because it's a vector and we are trying to calculate the scalar value, and that will become you know, H of x by W. Or we have done something wrong here. XP is right. Okay. W transpose XP. Yeah. So R becomes H of X by mod W. W transpose is nothing but W dot product of W into R. And when W comes down, this becomes H of X by W. Okay. So that is what we have written. So the distance of a point from the distance of a point to the hyperplane will always be equal to this one. So let's call this distance as R. Then R can be written as H of X by W. X is nothing but the support vector. Okay. So that's how we calculated R, the distance. So now what is our criteria? Our criteria is to maximize that R. Okay. So we are trying to maximize the R now, right? So how do we, the object now turned down to maximizing that R. R can be written as H of X. X is the point from which you're calculating the distance to the hyperplane. Okay. Now let's put that down to some equation stuff. Let me erase everything. So okay. So this is how we calculated the distance of a point from that particular point. Okay. Right. So now we know the distance of a point from the point from that particular point, right? Now coming back to this R, you are trying to maximize this R. The goal for us now is maximize R. Okay. Now H of X can be written like this, right? So R can be written as H of X. Okay. Um, H of X can be written as W transpose X plus B or W into dot product of X plus B. Okay. H of X can be written like this by modulus of W. And now I already spoke about this particular stuff, right? So what is that? If you we know the every hyperplane H of X is equal to 0 here, and above that hyperplane H of X is greater than 0, and below that hyperplane H of X is less than 0. And I told for one of the class yi is equal to +1, and for the other class we represent that with label -1. And now we can combine these equations and write this as y into H of X is greater than 0. This is what greater than or equal to 0. So this is what we discussed right now. Even if you calculate from this side, this distance will become negative, right? Because H of X is less than 0. And now if you H of X is less than 0, so this becomes negative. If you want to make both the terms positive, we just have to multiply this y with yi. So we are talking about R. R is a scalar value. R can never be negative. But H of X for points below the hyperplane will always be less than 0. For the points above the hyperplane, H of X is always greater than 0. But we don't want R to be a negative value, right? So if you multiply that with that particular class, what happens? For these points, yi is equal to -1, right? For these points, yi is equal to +1. So now what happens? H of X is negative for these points, but when it is multiplied with yi, my negative into negative will become positive. Okay, so this is the now if you want to make this as a positive term, we are getting this as we're just multiplying this with yi. So now the R becomes yi into w in dot x plus b by modulus of w. Okay, this is what we have got now, right? Now when I say maximizing R, now let's get rid of everything, and now let's just focus on only this particular term. Okay, you understood how we derived this R? How the R value is derived? Are you clear with this? Okay. Now let's get rid of this diagram, and let's focus on the objective now. Okay. So I'll just erase some part of it, not everything. So these points we don't need for this point. Okay. So let me clear this stuff so you'll understand that. Now what I'm trying to do here is that it's as simple as this. We have the hyperplane here anyways. Now we got r as, now what we have got, r is equal to w dot x plus b into yi by modulus of w. So this is what we are trying to maximize. We are trying to maximize this term r. Okay. Now I'm at, this is the actual formula that we are trying to maximize. Now I'm adding a constraint for this. What I'm trying to add a constraint, the constraint is that I will make sure that the distance from this to this is equal to, I'm trying to like scale this such that yi into w of xi plus b is greater than or equal to 1. Okay, that means the minimum distance from the hyperplane to the support vector, now we are making that as 1. We are just scaling that distance so that we are just trying to make this as, even this distance is 0.5, we are trying to scale that so that the points will move further such that the distance from the hyperplane to the margin is coming down to 1. It's in mathematical terms, we are trying to make this point as 1. Okay, basically greater than or equal to 1. Okay, so that is what the constraints we have added. So we are trying to make sure, we are trying to make or scale the numerator to be greater than or equal to 1. So now what does r becomes? R becomes 1 by modulus of w. That means every other term is, distance is greater than 1, but only the points, the support vectors, okay, will have, you know, um, are at distance 1. I would say that's what it basically means. So the, now we are adding a constraint. That constraint is nothing but we are trying to make this numerator is equal to 1. Okay, when we are trying to make that numerator 1 or greater than or equal to 1, so what happens, this is the constraint we have added. We are converting the numerator to 1 now. So every point beyond this line should have distance from the hyperplane as greater than 1, whereas the point which is the support vector or the line passing through this particular intercepted line to the support vector is at distance 1 from the hyperplane. That is what we are trying to make up here. Okay, now when we added this constraint, what we are saying is that we are trying to make sure every point is above, is greater than or equal to 1 from the hyperplane. Okay, from the hyperplane every point is at a distance of greater than or equal to 1. Okay, so that basically turns down to this particular equation. So now we are making the numerator as 1 and we are trying to add this constraint for every point. This applies for every point. Every point distance is greater than 1, greater than or equal to 1. So what is the point which is close to the hyperplane? That is the support vector. So the minimum distance from the minimum, the point which is close to the hyperplane should have distance 1. So every other point should have distance greater than or equal to 1. So that is the constraint we will add so that this equation r will turn down to 1 by mod w. Okay. Just a second. So do you remember this particular slide that we were talking earlier, which is, so that would be a good example for you to get memorized here. So I was talking about two lines which are parallel to each other and can be represented as +1 and -1. Is there of something? That's all. So let's come back to this slide back again. Let me try to bring up it here. So now we are just adding a constraint for every point. Okay. So we are saying that this is the distance wx. This x is the support vector here, right? X is the support vector. So this x here is a support vector. In this case, r is the distance of the support vector from the hyperplane. So that is called as margin. So this x is the support vector. Now what we are saying, we are trying to scale this such that the support vector will be at the distance of 1 from the hyperplane. Okay, so this, let's suppose this is the factor of the distance. So yi w into xi plus b is a factor of the distance. It is the distance is proportional to this term. Weight vector will always be constant, right? This weight vector is coming from the hyperplane parameters. Okay, so x is the factor that decides the distance from a particular point. So in this case, the distance parameter that is actually deciding is x. So x is the point which tells the distance from the point. Okay, so here x is the support vector point. So when we say support vector is kept at a distance 1, every other point above this support vector will have wx plus b into ya is greater than or equal to 1. Right? When support vector is at 1, every other point will have the distance greater than or equal to 1, a factor proportional to distance. This is not a distance, complete distance. Distance is just, we just need to divide this by mod w. But what we are trying to do is, we are just trying to scale the numerator such that every point will have a distance greater than or equal to 1. When I say distance, it's a fraction proportion of the distance. If you look at the distance of any point to the hyperplane, the formula is given as w into x plus b by b into yi by mod w, right? So w doesn't decide the distance. W will always be constant for every point because w is derived from the hyperplane. What is the hyperplane equation? W h of x is equal to w transpose x plus b, right? That w is the hyperplane parameter. So what is the only thing that decides? That decides is x. So if there is a point here, this point's distance from to the hyperplane is dependent on x. Okay. So let's suppose this x is marked as 5 and this x is marked as 2. So this distance, this 2 only will change for these two things. So if I write this comes w into 2 plus b into yi by mod w. So for this point, this becomes w into 5 plus b into yi. So what is the only thing that is changing? Only x is changing, right? So the only parameter, the only fraction that decides the distance is w into x plus b. So now what I'm saying, this constants actually says we are adding n constants here. N constants means n points. For every point, we are adding a constant. And that constant says that every point distance from the hyperplane is greater than or equal to 1. Okay, that means only the support vector will have distance 1. Every other point will have distance greater than or equal to 1. Okay, so now we added that constraint by just doing some factor multiplication, or by normalization, or some sort of, we just multiply this by 1 by w x plus b into ya, so that this becomes 1 on the top. Okay, so that is the constraint we are adding. That constraint is this one. So this constraint says every point is distance is greater than or equal to 1. Now that this is that constraint. Now we have r is equal to 1 by mod w with n constants. Each constant says with n constants. This is n constraint problem. What are the n constants? We are adding one constraint for each point. That is yi for every point, yi into wi, w. So this just becomes w because weight vector is dependent on the hyperplane. So this becomes w, yi into w of xi, yi into w of xi plus b is greater than or equal to 1. That means every point distance from the hyperplane is greater than or equal to 1. Which points will have distance equal to 1? The support vectors will have distance 1. Every other point other than support vectors will have distance greater than or equal to 1. Okay, so that is what this actually, this objective basically means is. Okay, so this says Now we started from here. We found out that the vector r can be written as the distance r is 1 by mod w, and we added n constants. This is an n constraint problem. What are the n constants? We say that every point's distance from the hyperplane is greater than or equal to 1. So every point for n points, okay, we are adding this constants yi into w of xi plus b, which is the numerator term, is greater than or equal to 1. When I say greater than or equal to 1, the support vector's distance from the hyperplane will be equal to 1, and every other point other than the support vector's distance is greater than 1. Okay. For all I means every point in the 2D space that is given for us, or in the space that is given for us. That is what the objective function mathematical representation is. Now take this term r is equal to 1 by w. We are trying to maximize the margin. Okay. We are trying to maximize this margin. Maximize. So this is a maximization problem, right? I'm returning that into minimize modulus of w. Okay. So maximizing 1 by w is nothing but minimizing the w. When we minimize w, this becomes maximization problem, right? So maximizing 1 by w is equal to minimizing w. Okay. So that it simply can be understood 1 by 2, 1 by 5. Okay. So 1 by 2 value is 0.5, right? This is 0.2. What is happening? We are maximizing. Sorry, it's a written down. So we are maximizing. So when we are maximizing, when we are minimizing the denominator, we are maximizing the value, right? The denominator is w. When we are minimizing this w from 5 to 2, we are maximizing the overall value. Similarly, if you want to maximize 1 by w, we have to minimize w. Okay. So now the objective is turning down to a minimization problem from a maximization problem when we converted the denominator and numerator. So minimizing w is nothing but minimization of w square, right? When we try to minimize w square, it is nothing but it is proportional to minimizing w. So why we are squaring this? For mathematical convenience, we are just squaring this because we don't want roots to be coming up. Because w is nothing but what is w? W is nothing but root of w1 square plus w2 square plus w3 square, right? That is what w vector is, right? W is nothing but h of x is equal to w transpose x plus b. If you expand this, what does this turns down to? It turns down to w1 x1 plus w2 x2 plus w3 x3 plus so on plus wn xn plus b, right? That is what h of x representation is. Now, if you take the modulus of w, that turns down to root of w1 square plus w2 square plus w3 square, right? So we don't want to continue or do complex mathematical calculations with square root. So that for mathematical convenience, we are just squaring that, so that it just turns down to sum of squares problem. Okay. So there is no harm in just squaring the value. Minimization of w is nothing but is proportional to minimization of w square. And again, for just mathematical convenience, I'm just adding 1 by 2 as well to just minimize the impact of w2 square, and also for mathematical convenience. Let's suppose the actual objective is w, right? Let's suppose the value of w is, let's take it as 5. Okay. So we want to minimize the value of w, right? So w, let's suppose w is equal to, let's take a simple number, w is equal to 2. W square will become 4. 4 by 2 is turning down to 2 again. Okay. So we are just doing half for it, w square by half. When we want to minimize w, it can be turned down to, it is proportional to minimizing w square by 2. That's what I'm trying to say. Minimizing w is nothing but minimizing w square. These two are proportional, and minimizing w square by 2. All these three will be proportional. Okay, it does not impact the objective. Okay, just for example, if w is equal to 2 here, We are trying to minimize this value of W2. So this becomes 4. 4 by 2 is turning down to 2 again. So these two are equal. Let's take another number 3. 3 square 9 by 2, which is 4.5. But W is 3. So it is just bringing down close to the original problem. We are doing this stuff only for mathematical convenience. Okay, squaring to get rid of the square root when we take the modulus of the weight vector, and 1 by 2 is just for mathematical convenience. You will understand this shortly why we are just doing 1 by 2, so that when we take the derivative of this, what this turns down to, let's suppose we are talking about maximization and minimization problems here, right? So maximization and minimization problems, the optimization problems we call them as, so we always take derivatives to get the optimal value of the W, right? When in maximization and minimization problems, we already discussed about that. So when you're trying to find the maximum or minimum value, you take the derivative and then equate that to 0. So what happens when you take the derivative of this 2W, it becomes 2W, right? So to get rid of this 2, we are just multiplying this with 1 by 2 so that these 2 will get cancelled in future. So there is no harm if you just try to multiply this with 1 by 2, because the objective is just to minimize this W. So you can do square root, cube root, or whatever it is. Everything will give a proportional result. So that is what actual objective right now is minimize W and B. Minimize for every W and B, for these are the hyperplane parameters W and B. Minimize 1 by 2 W square given n constants. What are the n constants that we have introduced by making the numerator as 1? That is yi into W of xy plus B is greater than or equal to 1. Okay, so this is called as primal formulation of SVM. Okay, this is the primal objective. So there will be two forms. One is primal form and the other one is dual form. Primal form is just a normal form that we derived. Dual form is derive when we derive something from the primal form, from the primary objective of any model, we call that as dual form. Okay, we will actually see the dual form shortly. So this is called the primal formulation of support vector machine. What is support vector machine trying to do? Support vector machine is trying to find out an optimal hyperplane that separates two classes with maximum margin. Okay, we are trying to maximize the margin between the support vectors. Okay, or maximize the margin uh, from the support vector to the hyperplane. Margin is nothing but the distance of the support vector from the hyperplane. We are trying to maximize that. That distance is nothing but 1 by yi into w, w of xi plus b by mod w is the distance of the distance of point or the support vector from the hyperplane. Now we made this numerator equal to 1 by adding n constants. What are the n constants? N constant says that the proportional distance from the point, from any point to the hyperplane is always greater than or equal to 1. When we say every point's distance is greater than or equal to 1, so what is the closest point to the hyperplane? The closest point to the hyperplane is support vector. So the closest, when we say everything is greater than or equal to 1, the closest point will be at the distance 1, and every other point will be at distance greater than or equal to 1. So we added n constants and we made the numerator as 1. Now we converted maximization problem to minimization problem. So maximizing 1 by W is equal to minimizing 1 by W. Now for mathematical convenience, we changed that minimization of W problem to minimization of 1 by 2 into W square. Okay. So these two results are proportional to each other. Minimizing W is nothing but minimizing W square will also be proportional to that particular value. So that is what primal formulation for SVM basically means is. So what is the primal formulation now? Primal formulation says the optimization problem, the primal formulation of SVM is minimizing 1 by 2 into W square with n constants. What are the n constants? The distance of every point, the proportional distance of every point from the hyperplane should be greater than or equal to 1, which is yi into W of xi plus b is greater than or equal to 1. So now let's come back. W is the weight vector. Okay. B is the bias. You already know what is a bias. We discussed by changing the value of bias, how the values are moving. How the values are moving. You have, we studied this, right? Y is equal to minus a plus minus b. Y is equal to what is that? Minus ax minus c by b by b. How did the lines change? By changing the value of a, by changing the value of c, and by changing the value of b. B will impact both slope and intercept. Value changing the value of C changes the intercept. A will change the slope of the line. We already discussed that stuff. Okay. Xi is the input data point. Yi are the class labels, either +1 or -1. So when you by now you would have understood that SVM will do binary classification. It can differentiate only two classes. Okay. So it can classify only if the data set has two classes. So one class can be written as one, or one class can be written as -1. So it can classify whether it is dog or cat only. It cannot classify dog, cat, or lion. Okay, it's a binary classifier. SVM is. SVM is basically used for binary classification. If you want to classify multi-class classifications, we already talked about this, right? One versus one versus many approach. Okay. So if you have to do multi-class classifications, you have to combine multiple SVMs and do that result and get the answers. Okay. So this is what the primal formulation for SVM is. Is this clear, or do you uh, have you got confused anywhere? Hello.
Clear.
Okay. So you just understand this. W is an unknown parameter. B is unknown parameter. Xi is input points. This is known. Yi is known. Why Xi and Ia is known? Because you will be given a data set, right? In this data set, let's suppose these are all the features of the dog and this is Yi. So this is all Xi. Okay. Xi is nothing but a vector or animal features. This can be tail size, color, and what we call it as um, color of the dog, color and size or height or something. Some parameters that distinguish. So these are all Xi and this is Yi. So if this is dog and if this is a parameter of cat, and if you have another point as dog, another point as cat, let's suppose 1 2 3 1 1 2 1 2 4 1 1 1. Okay, so this is the data matrix that is given to you. And now YA is given to you. YA is given as dog and the YA is given as cat. So SVM can only use to classify two classes, spam or no spam, dog or cat. So now in this case, we consider dog as +1 and cat as -1. So you know Y. Y is from the data matrix and you also know XI. What you're trying to determine, you're trying to determine W and B, which is the hyperplane parameters. Your main goal is to find out hyperplane. Hyperplane is nothing but W transpose X plus B. In this, what you don't know W and X. Okay. So you're trying to find out that. So that's the reason W and B are unknown. You're trying to find out the values of W and B. Okay. Using this optimization problem. What is this optimization problem? Optimization is minimizing W of 1 by 2 into W square given n constraints. How do we solve this optimization problem and how do we get W and B is something that we will study shortly. Okay. Now solving the primal formulation. Now the objective for us is given as minimizing the modulus of W square by 2 given n constraints. What are the n constraints? N constraints is Yi into W of Xi plus B is greater than or equal to 1. These are the n constraints. Okay. For every point in the data set, we are adding one constraint. Okay. That is what it is. That is what we have discussed so far. We are adding one constraint for every point. What does that mean? Every point should have distance greater than or equal to 1 from the hyperplane. Only the support vectors will have distance 1. Every other point will have distance greater than or equal to 1. When we multiplied that with Yi, which is the class indicator, every negative will also become positive. So everything will become positive now. If you want to solve this using Lagrangian multipliers, if you want to solve this optimization problem, you have to introduce Lagrangian multipliers. So one Lagrangian multiplier for every point. So you have to introduce n Lagrangian multipliers, right? One Lagrangian multiplier for each point. So that turns down to, this is an n constant problem. So we have to run I for every point in the data set. So that's the reason we are doing the summation from I is equal to 1 to n, and we added Lagrangian multiplier to the constraint, and the original problem is this modulus of w square by the 2 minus. Okay, we already talked about solving using Lagrangian multipliers. You have to take the original problem and then add Lagrangian multiplier for the constraints and write that as a single equation. Now this became the actual equation that you want to solve now. Okay, once you have written this equation, what you have to do, you have to take the derivative with respect to w, with respect to b, and with respect to alpha I. That is how you solve the optimization problems, right? By introducing Lagrangian multipliers. We already have done this for where all we have done this. We have done this for LDA, linear discriminant analysis. Have we done that? For PCA, have you remember that? Introduced Lagrangian multipliers and then solved for the optimization problem. In PCA, do you remember? That's how we shown that um, the eigenvectors are the principal component vectors, or the principal components. We have derived that, right? In PCA, principal component analysis, right or
Yeah.
not? Yeah.
Yes.
Yeah.
XYZ partition particular derivation.
Yeah, and then we derived using all the variables W, B, and alpha. So the same thing we will do it here as well. Even for any optimization problem, we do solve the same things. So when you have constraint problem, introduce Lagrangian multiplier for all the constraints. Here we have n constraints. There we have just one constraint. Here we have n constraints. So we introduce Lagrangian multiplier for every constraint, and we came up with one optimization formulation, and then we derive this formulation with all the variables, and using those derivations we conclude the values for the Lagrangian multipliers. Okay, now we have only one constraint. Now that constraint is alpha I is greater than or equal to 0 for every. So now we converted the constraint problem to unconstrained problem. This is unconstrained problem, and the only thing is alpha I is greater than or equal to 0 for I mean the Lagrangian multiplier is always greater than or equal to 0. Okay, um, and this comes from KKT conditions. We will discuss this shortly about this alpha, why this alpha is always greater than or equal to 0. I'll show you that shortly. But now the next step is to take the derivative of this equation with respect to W and see what is happening with respect to B, and see what is happening when with respect to alpha, and see what is happening. Okay. Now to solve that unconstrained problem, we are taking the derivative with respect to W. So let's take the derivative with respect to W and see what is happening. Dou of LP by dou of W. Okay. So let's solve this equation, and let's see. I'm just moving this one from this side to this side. Okay. So if you want to convert this greater than or equal to 1, I'm just moving this to this side so that this becomes alpha I W of xi plus b minus 1. So 1 on the right hand side is turning down to minus 1 on the left hand side. So now it's as simple as this. Now if you expand this equation, what this turns down to 1 by 2 W square minus sigma I is equal to 1 to n. Break down these formulas. Okay, break down everything and write it as individual terms. Y alpha I yi w xi. Okay, so this is one term, and alpha I yi b minus sigma I is equal to 1 to n alpha I yi b. Okay, my minus into minus will become plus, plus I is equal to 1 to n. This becomes alpha I. Okay, that is all what it actually turns down to. Okay, so now we broke down everything into a single equation. Now we are going to take Now we are going to take the derivative of these things uh, and see what is happening. So now this is the whole equation for us. Now let's take the derivative of this. So what we have done here, we have broken down this large equation into simple terms, right? 1 by 2 alpha square is remaining the same, minus I equal to 1 to n alpha ya. This becomes ya w xi plus b plus ya into b, right? Ya is multiplied with both these things. So now we multiply alpha I for both the terms, and minus 1 will also be multiplied with alpha 1. So now this is the first term, this is the first term, this is the second term, and this is the last term. Now we got this equation. Now if you take the derivative of this equation with respect to w, okay, so if you derive this with respect to w, what becomes? So w square will become 2w as you are taking the derivative with respect to w. 2w is equal to, so w is there, so now we can convert this to this w will be, as w is there, everything is else is constant, this turns down to ya alpha I xi. Okay, so as w is there, this becomes 1. So there is no w here, it becomes 0. There is no w here, it becomes 0. Okay, now 2 and 2 will get cancelled. That's the reason why we added 1 by 2 for the minimization problem, for simplifications, for mathematical convenience. So now this whole term will turns down to w minus sigma I is equal to 1 to n alpha I yi xi. Okay, so now we can write this as w is equal to sigma I is equal to 1 to n alpha I yi xi. Okay, so now this is what w is. Okay, this is what w is. That we are done with that. Now let's take the derivative with respect to b. Okay, take the derivative with respect to b. LP by derivative with respect to b. What happens if we take the derivative with respect to b? Let's see. Again, coming back, there is no b here, so it becomes 0. There is no b here, it becomes 0. So if you take this turns down to, as b is there here, it becomes sigma I is equal to 1 to n alpha I yi. Okay, so there is no b here, and there is no b here in the last term as well, so this becomes 0. So now we can write this as the second thing that we came up with when we take the derivative with respect to b is I is equal to 1 to n alpha I yi is equal to 0. Okay, so this is what we came up with. So these are the two equations when we take the derivative from these two equations. So now if you take this, when you take the derivative with respect to w, we got this. Okay, so that is what I have shown you in the previous slide. So this is what we have got. W is equal to sigma I is equal to 1 to n alpha I yi into xi. Now from this, what you can understand is that weight vector is nothing but the linear summation of all the points, right? We are just doing summation of all the points with some factor multiplied to that, which is the Lagrangian multiplier. So w is nothing but the linear combination of all the points. That's something you can say. When you derive with respect to b, what you have got, you have got this result, sigma alpha into ya is equal to 0. Okay, so this gives us a condition that sum of Lagrangian multipliers is equal to 0. Okay, ya is just an class parameter, right? It is just minus or plus 1. So alpha I is equal to 1 to n alpha I yi is equal to 0, right? So if you want to write this in a different format, what is that? So you can write this in a different format, right? So it is nothing but alpha is equal to 1 to n yi for class 1, which is positive 1 alpha I, minus, because for the other points ya is equal to minus 1, for all the points that belongs to ya is equal to minus 1, is equal to into alpha I is equal to 0. Okay, alpha I into yi for points that belongs to -1 class, okay, will have minus coming down, because so alpha into -1 will become -1 into alpha 1. Okay, so all these points belongs to -1 class, all these points belongs to +1 class, so that's the reason you got minus before this points. Okay, right, so we are just yi is positive for this, so yi into positive will become positive for these points. I'm breaking down these points to two things. One is class 1 points and the other one is class -1 points. So for class 1 points, you won't get any negative before them, because alpha ya is 1 multiplied by alpha a will become alpha a. For the negative class, alpha I into -1 become minus alpha I. So I'm just moving this minus to the outside of the summation, and I'm writing this like sigma is equal to 1 to n alpha I that belongs to y equal to -1. Now you say summation of the Lagrangian multipliers for all the points where class is equal to 1 is equal to sum of the Lagrangian multipliers for all the points where class is equal to -1. I'm moving this term to the other side, so that becomes equal to, okay. So this is one of the important observations or derivations that I came forward with. What this says, all the points, all the points above that hyperplane or belonging to a particular class, the summation of the Lagrangian multipliers introduced for all these classes is equal to the sum of the Lagrangian multipliers of the other class, which is -1. These two are canceling each other, right? That is what. So the summation of this is equal to summation of this. When we subtract both of them, we are getting to 0. So those two are canceling each other. So that is what this actually says for us. Okay. Now, so those are the two observations that we have got for now. Okay. Um, so what we are trying to solve here, we are trying to solve for the value of w. Our main goal with these objective functions and all this stuff is to find out the hyperplane, which is h of x. Okay, this is the hyperplane, the separating hyperplane. We are trying to find out this equation, which is w transpose x plus b. Okay, we are trying to find out this hyperplane w transpose x plus b. We are trying to find out w and b. That is the whole intention of doing all this stuff. So finally, we have to derive what is w and what is b, but we haven't derived W and B. So far, what we have found out for now, W is nothing but the summation of all the points in the space, right? It can be derived, W can be written as the summation of all points. Okay, and you also find out that Lagrangian multipliers that you introduced for the points will cancel each other. For the positive class and negative class will be equal, and they cancel each other. Okay, let's, before going further and trying to, before trying to solve the W and B, let's find out few more interesting facts about the support vector machines. So for that, you have to understand this simple concept, which is KKT conditions. What this KKT condition says is that these are set of mathematical prerequisites necessary for finding the optimal solutions in nonlinear programming problems. Okay, in the nonlinear spaces, KKT conditions says, KKT conditions will say three, will it has given us four different conditions. Okay, in the optimization problem, optimization is nothing but finding out the maximum values or minimum values for a particular value for or a particular variables. So what does KKT condition says is that convert the Lagrangian function and derive with respect to variables and equate to 0. That is what we have doing, right? We converted to Lagrangian function. For the constants, we introduced Lagrangian multipliers, and we then taking derivatives with respect to each variable and equating them to 0. And the second condition that it is saying is hi is the constant, alpha I is the Lagrangian multiplier. What it says, when we multiply the Lagrangian multiplier with the constraint, that will become equal to 0 in the optimal solution. Okay, so KKT conditions will be applied only for convex problems. Convex problems means the curves will basically looks like this. There will be only one local minimum, okay, or one local maximum. So those problems are called as convex problems. Okay. So these graphs will not be like this. Okay. There won't be there won't be many local minimums and or local maximums. There will be only one local minimum or local maximum which is equal to the global maximum. So in this course, SVM is such kind of problem. Okay. Um, so we can, the KKT conditions will apply in that case. So alpha E into HI is equal to 0. HI is less than or equal to 0. That means constraint will always be less than or equal to 0. And Lagrangian multiplier is always greater than or equal to 0. So that alpha I greater than or equal to 0 is came from Lagrangian KKT conditions. Okay. So these are the KKT conditions, experimental results. So you are not going to derive or show these derivations and all that stuff. You just have to, I mean, accept these facts given by those three scientists. That is called as Karush-Kuhn-Tucker conditions. Okay. So it's simple. First thing is they have given four conditions. The first condition is derive them with respect to the variables and equate them to zero. Okay, and then they have given that the Lagrangian multiplier multiplied with constant will always be equal to zero, and always the Lagrangian multipliers will be greater than or equal to zero, and the constants are always less than or equal to zero. Okay, so now let's understand this with an example. Now, given this is the optimization function, and you're trying to optimize this using these constraints. Okay, then what you will do, you will add constraints for every, you know, you will add constraints for every, I mean, Lagrangian multiplier for every constraint. So this is the equation, and Lagrangian multiplier constraint added for this, and second, for the second equation, you added another Lagrangian multiplier. So these are like, you don't add when we say that's something greater than or equal to zero. You can use them when you are actually finding out the values for alpha I and xi. Okay. Now take the derivative with respect to alpha with respect to x1. Okay. Now I have taken derivative with respect to x1. So I have taken derivative of this. So that turns down to, we consider only x1 terms. So x1 square will become 2 minus 2 into x1. And we don't have x1 here. This goes to 0. This goes to 0. And 4 into x1 will become minus plus 4. And x1 is there here minus lambda 1. And x1 is there here minus 2 into lambda 2. So that's how you take the derivative with respect to all the variables. That is the first condition of the KKT conditions, right? Take the derivative of all the conditions. And what is the second condition it is giving? It is called as complementary slackness. Complementary slackness is nothing but Lagrangian multiplier multiplied with the constraint. What is the constraint here? This is the constraint. Okay. So this is the constraint. X1 plus x2 less than or equal to 2. Okay. This is constraint 2. And these are the restrictions on the values. So now the constraint 1 alpha 1 into x1 plus x2 minus 2 is equal to 0. Alpha 2 into 2x1 plus 3x2 minus 12 equal to 0. So this is the second KKT condition given. Third KKT condition says the constraint is always less than or equal to 0. And the fourth condition says alpha 1, alpha I is greater than or equal to 0, and alpha 2 is also greater than or equal to 0. Okay. Now using these conditions, we will try to find out the values for x1 and x2. Okay. It's just like a sample mathematical equation that we are going to solve now. Okay. We are not going to solve anything beyond that. It can be simply found out basically. So convert everything into x. Here you have x1, x2 terms, right? Now you have these conditions as well. X1 plus x2 minus 2 is always less than or equal to 0. Find out, you can find out the values of x1, x2. It's just solving all these equations together. Okay. Either you can derive lambda 1, lambda 2 out of this, or x1, x2 out of this, and substitute in these, or do vice versa stuff and all those things. Okay. So just we are not interested to solve these problems anyways. When we do the programming, we never solve the equations and all that stuff, but just understand what does KKT says. KKT condition says, KKT condition says gave us four conditions. The first condition is take the derivative to solve our primary objective is to solve the values of x1, x2, x3. Okay. For solving those values, you can consider the KKT conditions in the for the in the optimization problems. It says first take the derivative with respect to every variable. Use that as first condition. The second condition says Lagrangian multiplier multiplied by the constraint is equal to 0. So we introduce two Lagrangian multipliers for the two constraints. So lambda 1, lambda 2. So these two terms will be equal to 0 at optimal solution. And the third thing is primal feasibility. That means the constraint will always be less than or equal to 0. And the second one is dual feasibility, where alpha 1 and alpha 2 is greater than or equal to 0. Lagrangian multipliers are greater than or equal to 0. Complete snackless, primal feasibility, and dual feasibility, Lagrangian and derivative. These are the KKT conditions. So we learned we learned the four conditions and we accepted them. But now, how do we use them in our derivation? Is that now just look at this. Now, using the KKT conditions, what is the constraint that we do have? The constraint that we do have is alpha I into W of xi plus b is greater than or equal to 0. That is the constraints we do have for our primal problem solvation, right? So now if I introduce a Lagrangian multiplier for this, okay, so this is our problem, optimization problem. Now I have a constraint. And if I introduce a lambda I, which is Lagrangian multiplier for this, and using KKT conditions, what does this says is that this should be equal to 0. This is the slack completeness or complementary slackness. Okay. So now constraint multiplied by the lambda equation is equal to 0. That is what it is saying, right? This implies that alpha I is greater than or equal to 0. The point xi lies exactly on the margin. For other points, alpha is equal to 0 or not on the margin. Okay, this is very important thing that you have to understand. Now, this is something that we derived from KKT conditions, right? Okay, this is something that we derived from KKT conditions. Alpha I into yi w of xi plus b minus 1 is equal to 0. But now when we introduce these constraints, thing that I have said is that if this is an optimal hyperplane, let me erase this and carefully understand this. This is an important point that actually decides the entire SVM things. So this is the KKT condition that we have derived. Now, what I have said, if I have a hyperplane like this, when we are introducing that constraint, we said that only the support vectors will be at a distance of 1 from the hyperplane. Only for the support vectors, we said wi into we added this constraint w of xi plus b is greater than or equal to 1. Okay, that means support vector will be at distance 1 and every other point will be greater than or equal to 1. Let's suppose if there is a support vector here, there is a support vector here on the same line, on the line intercepting the support vector. If we found out 3 points and if we have 3 support vectors for a single class, all these support vectors will be at a distance 1. Okay, that means any point that is lying on this line will be at distance 1 and every other point will be at a distance greater than or equal to 1, a proportional distance. Again, I'm saying if you have to get the actual distance, we just have to divide that with mod w, and that is just nothing but a factorization. W is a scalar value, right? Weight vector modulus is a scalar value that doesn't actually make you more sense of keeping that on both sides. Okay, even if you take the numerator, if you look at this, if you introduce w on both sides, it would be the same. You can just cancel them. You can just consider the numerators. That's okay. Now, what I'm trying to convey here is that for support vectors, yi w of xi plus p is equal to 1. Okay, for any point which is not a support vector, this value is greater than 1 because the proportional distance of any other point apart from the support vectors is greater than 1 because they are far away from this. That's how we scaled the constraint problem, right? Now, Have you understood these two things? Support vector will be at a distance 1 and other vectors will be at distance greater than 1. Is that clear? This thing. Hello.
Hello.
Yeah, is that clear?
Yeah.
Okay. Now, now, um, now if you do this stuff, now let's break down this. Let's find out this for support vectors. We know for support vectors, this is equal to 0. So I'm just trying to convert this to for support vectors. I'm trying to find out for support vectors now. For support vectors, yiw of xi plus b is equal to 1, right? So the whole term is becoming 0. So when this is becoming 0, alpha I necessarily doesn't needs to be 0. Alpha I can be greater than or equal to 0, right? Alpha I, there is no strict condition that alpha I has to be 0, right? If you take non-support vectors, if you talk about non-support vectors, you'll get some clarity. For non-support vectors, yiw of xi plus b is greater than yiw of xi plus b is greater than 1. Is that right? yiw of xi plus b is greater than 1 for non-support vectors, right? So this total value
Yes.
is greater than 1, right? Or greater than 0. This value is greater
Greater
than,
than 1.
so anything greater than 1 minus 1 will be a positive value. So in this case, for non-support vectors, alpha I must be equal to 0 for this whole stuff to be equal to 0. Correct? So if you talk about this equation for non-support vectors, yi into w of xi plus b is greater than 1. Okay. What does that mean is that this is not a 0 term. So this will not be equal to 0 for non-support vectors because this value is greater than 1. Greater than 1 minus 1 will be a positive value. So for this whole equation to be equal to 0, alpha I must be equal to 0, right? For non-support vectors, then only this whole term will be equal to 0. So for non-support vectors, there is no option for alpha I to be other than 0. Alpha I must be 0 for non-support vectors. But for support vectors, this term is equal to 0. So there is no necessary that alpha I should be equal to 0 for non-support vectors. Support vectors are the points that lies on these intercepted lines, which is a distance 1 from the hyperplane. Okay, so that is the important observation. The observation says that the support vector, the Lagrangian multiplier value alpha I is equal to 0 for the points not on the margin. Okay, this implies that if alpha is greater than 0, the points xi lies exactly on the margin. Okay, so if alpha I is greater than, for these points alpha I can be greater than or equal to 0. So in rare cases we get alpha I equal to 0 for non-support, for support vectors. So alpha for support vectors we can say alpha is greater than 0. For non-support vectors we can say alpha is equal to 0, which are not on the margin. For the points which are not on the margin, alpha is equal to 0. Okay, so that is one of the important observations that you have to find out. Understood this? Using KKT conditions, we found out two things. The first thing is alpha I is equal to 0 for all non-support vectors. Alpha is greater than 0 for support vectors. Okay. Now, coming back to this W that we have found, W now has, we have to, when we are talking about W, we said that W is nothing but a linear summation of all the points. Now, for non-support vectors, alpha I is 0. So now W is just the linear combination of only support vectors. Okay, because alpha is non-zero for only support vectors. Now you can conclude that W is determined only by the support vectors. Okay, which are not support vectors are not determining W. Okay, if any other points other than support vectors, they are not influencing, they are not showing any impact on the, they're not showing any impact on this hyperplane. Okay, what are the only vectors that show impact on the hyperplane? Are the support vectors, because only for those vectors you have alpha I greater than 0. For in every other point you have alpha equal to 0. So they are not contributing to the weight vector of this hyperplane. So what are the only vectors that are determining W? Only the support vectors are determining the W. From this you from this derivation you understood that W is nothing but the summation of all the vectors in the space, but xi is equal to 0, alpha I is equal to 0 for non-support vectors. Alpha is non-zero only for the support vectors. That means W is determined only by the support vectors. So other points will not have any impact on determining the value of W. Okay. So once W is determined, you just have to find out, once you have to find out the support vectors, and once you found out the support vectors, you just insert them here. Okay. Now the bias B is computed. How now you have to find out the W. Once W is found out, W is found out only by the support vectors. The summation of the, or the linear combination of the support vectors determines the W. And now how do we determine B? B is determined like this. Y is equal to W transpose X plus B. And from the support vector, you calculated W and take any of the support vectors. You can take any support vector. XS, you know that support vector point, you know the W, and you know the class of the support vector. Okay, if you're taking this cluster, this becomes +1, and if you're taking this support vector, it becomes -1. You know y as w xs, you can determine B by just subtracting ys minus w into xs. So that's how you determine B. That's how you overall compute W and B. Once you found out W and B, what you say, when you have to predict new value, W and B now. When you want to predict a new value, the class of a new point, just subtract, do the dot product with W, and just do the summation of B. If the total value is greater than 0, then that becomes to class 1. If that is less than 0, that becomes -1. So because you know h of x, you're trying to calculate h of x. If it is greater than 0, it is above that plane. And if it is less than 0, it is below that plane. That's how you do the predictions. But technically, these optimization problems cannot be solved on paper. Determining this alpha I, xi cannot be done on the cannot be done or shown on a paper. These can be solved only by utilities. Okay, the optimization solvers. We have specialized algorithms to do these optimization problems, or finding out the optimization values for different vectors. So that will be done by the specialized software. So you cannot show them on the paper. But what you have to, the takeaways here is that you understand what is optimization problem, and you understand what are the KKT conditions. How do we concluded that the alpha I value is 0 for non-support vectors, and alpha I, this is all intuition that we have talked about. We derived alpha is not 0 for support vectors, but alpha is equal to 0 for non-support vectors. You derived that, and you also found out that KKT conditions, from the KKT conditions you derived that stuff. And then you also found out that W is being contributed only by the support vectors. Non-support vectors has zero role in determining W, because alpha is equal to 0 for non-support vectors. And you also have seen how do we calculate B, and how do we determine if you're getting a new point using W and B. Okay, so you determine point as +1 if W transpose X plus B is greater than 0, because when h of x is greater than 0, it's above the hyperplane. If h of x is less than 0, it is below the hyperplane. Okay, so this is all about the primal formulation. And now you're trying to find out the dual, deriving the dual formulation for the support vector. Dual formulation, as I told you, dual formulation will be derived from the primal formulation. Okay, so this is the primal formulation, and if you're deriving anything from this primal formulation, that becomes dual. Okay, so in dual, what you will see is you will just only find out two things. You see this equation only in the terms of Lagrange and multipliers, and then you solve for the Lagrange and multipliers again using optimization solutions. Okay, this is a simple thing that I can just show you briefly. So now we are trying to solve. This is the primal equation you have got, right? This is the constraint. You introduce Lagrange and multiplier for that, and when you derive this primal formulation with respect to W, you got this equation with respect to W. When you derive that with respect to W, you got this equation. You got this W, and when you have done the derivation with respect to B, you got this, right? And now let's introduce these terms back again. See what how does this actually look like. Now again, I'm doing an expansion for this. This becomes modulus of W whole square minus sigma I is equal to 1 to n alpha I yi w xi. Okay, and then this becomes minus sigma I is equal to 1 to n alpha I yi b plus sigma I is equal to 1 to n alpha I. Okay, so this is all what we have got so far. Now I'm rewriting this equation 1 by 2 mod whole square minus, I'm taking this W outside. I'm taking this W outside, and now just observe this. I is equal to 1 to n. It don't have anything to do with summation, so I'm taking that down. Alpha I yi xi. Sigma I is equal to 1. So the rest of the term will become like this, minus sigma I is equal to 1 to n alpha I yi. Again, I'm bringing the b outside because b has nothing to do with the summation, plus sigma I is equal to 1 to n alpha I. Okay, that is what you have got when you expand that. Now if you carefully observe these things once, so again I'm writing this as 1 by 2 modulus of W square, okay, minus W into, look at this stuff, this is equal to W, right? W is nothing but sigma is equal to an alpha I yi xi. So I'm converting this to W minus B into sigma I is equal to 1 alpha and yi is equal to 0 from this. So I'm turning down this to 0 plus sigma I is equal to 1 to n alpha I. Okay. Now again this becomes 1 by 2 modulus of W square. This becomes W into W will become W square plus sigma I is equal to 1 to n alpha I. So I can rewrite this as sigma I is equal to 1 to n alpha I minus 1 by 2 modulus of W square. Okay. Have you understood this? Okay. 1 by 2 W square minus W square will become half W square. So this is nothing but sigma I is equal to 1 to n alpha I minus 1 by 2. W square can be written as W transpose W, right? W square is nothing but W transpose into W. Okay, in matrix notation. Now I'm converting this down to this way. Now let's focus just on W transpose and W. Okay, so W transpose into W is nothing but W is a vector, so that can be written like this. How can we write that? What I'm saying, W is nothing but, if you expand this term, let's take x as 2, n as 2. Okay, focus on this so that you will understand this equation. Now we are just trying to find out this particular equation. We are close to finding out this equation. Okay, now I have to show you that w square is nothing but, that's what we are here, right? W square, which can be written as W transpose, and W can be written like this. So I just want to show you this particular stuff to you now. That is equal to W square is equal to double summation. This is what I'm trying to show you now. Once you understand this stuff, you will understand what is dual formulation. Okay. Okay. All right. So I'm coming back here, going back here. Now I'm taking, just to show you the double summation, how does the double summation is happening. I'm just trying to take n is equal to 2. I'm just taking n is equal to 2. So now W can be written as sigma I is equal to 1 to 2 alpha I yi xi. Okay. So W can be written as alpha I y alpha 1 and y1 x1 plus alpha 2 y2 x2. Right? This is how I can write W. When I say vector multiplication, okay, when I say vector multiplication, how does that actually look like? If I want to write this in vector form, how can I write it? I can write it this way, right? If it is a matrix notation, or you can even doesn't need to go back to matrix notation. It's just W square, right? How does it actually looks like in W square notation? So in W square, it turns down to this one. Again, this multiplied with the same W, right? So W square is nothing but, it's simple. So W square is nothing but alpha 1 y1 x1 plus alpha 2 y2 x2 into alpha 1 y1 x1 plus alpha 2 y2 x2. Now if you look at this alpha is again getting multiplied with these two things, and this alpha is again getting multiplied with these two things. Okay, so if you have n terms, every term will get multiplied with this whole term, right? Now what I'm trying to do here is that this equation, the second W, I'm trying to write it this way: sigma z is equal to 1 to n alpha I yi x, I mean alpha j yj xj. Okay, so that is what I'm trying to find, do this for the inside vector. Now look at the terms. For this is also repeating, and every term is multiplying with every other term, right? So now what I can do, sigma outside, sigma I is equal to 1 to n, I can say alpha I yi xi. Okay, this is multiplying with this one. So now if I convert, I can convert this to this form, something like this. This becomes I is equal to 1 to n. I'm bringing the summation outside, 1 to j alpha I alpha j. I'm just bringing the summation outside. So this becomes alpha I yi xi alpha j yj xj. So putting down alpha i's and alpha i's at closest proximity, like I'm putting them together. So that becomes alpha I is equal to 1, j is equal to 1 to n. This becomes alpha I, alpha j, yi, yj, xi, xj. Okay. So now this is the dual formulation. Now if you try to expand this, it actually happens the same way. Okay. How does it actually happens? Um, Now let me take the same thing and let me do the expansion for this, so you will understand that is coming down to the same multiplication stuff. Okay, I'll just add a new slide and just show you, for you to get, I mean, to, you would be able to accept that once you do this derivation stuff. Now you got two terms. The first term is this one, Okay, the first term is this. So let's take this back there to the other slide and paste it there. Okay, so this is something that we have converted this equation, right? So we try to convert this equation to that. Let's do a small multiplication on both of them, and then you will understand that they both are equal. Okay, this is the other term that we got. Now we need to make sure these two multiplications are equal. Okay, let's go do that stuff, and let's back here. Okay, now I'm going to expand this. Let's apply only j now. Let's take n is equal to 2 again. I is equal to 1 to 2. Sigma j is equal to 1 to 2. And alpha I, alpha j, yi, yj, xi, xj. Right? So now apply summation of I is equal to 1 to 2. Alpha j is 1. So alpha 1, yi, y1, xi, x1. Okay, plus j is equal to 2. So that becomes alpha I, alpha 2, yi, y2, xi, x2. So we got this right. Now again, do everything again. So now replace I with 1 and I with 2. So now this is the whole term. Now apply 1 to it. So alpha 1, y1, y1, x1, x1. So applied I is equal to 1 in this term, and in this term also I'm applying y is equal to 1, I is equal to 1. This becomes alpha 1, alpha 2, y1, y2, x1, x2. Now replacing alpha 2 in this. So this becomes alpha 2, I is equal to 2. So this becomes alpha 2, sorry, alpha 1, y2, y1, x2, x1 plus alpha 2, alpha 2, y2, y2, x2, x2. We got four terms, right? Now if you do the multiplication here, alpha 1, y1, y1, x1, x1. If you multiply these two, now multiply these two things. This becomes alpha 1, alpha 2, y1, y2, x1, x2. Multiply these two. So this becomes alpha 2, alpha 1, y2, y1, x2, x1 plus multiply these two now. Alpha 2, alpha 2, y2, y2, x2, x2. So now if you look at this, these both are equal. That means these two are equal. Converting the square to double summation. Understood? So now this equation completely turning down to this equation completely turning down to this derivation completely turning down to this form, which is called as dual form of SVM. Okay, so this is the dual form of SVM, and we also have some conditions, which is alpha I y is equal to 0 and uh, alpha I is always greater than 0. That is the that condition is KKT condition, right? The Lagrange multiplication will always be greater than or equal to 0. Okay. Now the dual objective function we maximized. So this is a maximization problem. Okay. Primal problem is minimization problem. This is maximization problem. Dual form is, I'm saying it as maximize alpha. Why this is maximization problem and why that is minimization problem? Now let's understand that why we are saying dual formulation is maximization problem and that is minimization problem. Let's understand that so that we will be completing with the primal formulations and dual formulations. And just remember, primal formulation is minimization problem and this is maximization problem. So I'm saying this as a maximization problem. Okay, why this is maximization problem is what we are trying to understand now. So what we are trying to do in the primal problem, we are trying to minimize W square. Okay. So this equation is nothing but this equation is nothing but what is this equation came from? I is equal to 1 to n alpha I W square, right? W square, right? So this dual form can be written this way. So now our primal objective is to minimize this. When you minimize this, what this whole function becomes? This becomes maximization, right? So let's say the value of this is 100. Okay. When you say, when you're trying to minimize this, so let's take the value of W square as 50. Let's take the value of W square as 20. Let's take the W square as 10. So when you're decreasing the value of this, what is this becoming? 50, and this become 80, and this become 90. So minimizing this is nothing but maximizing this, right? So when you're minimizing this part, this is maximizing. So the whole function will become a maximization problem, because this is the minimization problem that we are trying to achieve. When we want to minimize this function, we want to maximize this whole function. That is the reason dual formulation is had become a maximization problem, whereas the primal problem is minimization problem. The primal problem is minimization problem, where we are trying to minimize W square with these constraints. But in dual formulation, W square on the other side, minus W square. So when you minimize this becomes a maximization problem. Understood? So that is the reason dual formulation is a maximization problem. Solving for alpha is performed using specialized optimization libraries or algorithms. So you got an optimization equation. Now you have to solve for alpha A, right? You cannot solve this on the papers. Okay. Your intention is to find out alpha A so that you will be able to find out W, and then using from the W you will be able to calculate the B, right, by taking one of the support vectors. So all that stuff, finding out the value with an example, cannot be shown on the papers. It has to be done by specialized libraries, optimization libraries or algorithms. In practice, what we have found out in form, we solve for W and B directly. So I have shown you introduced a Lagrangian multiplier, but most of the algorithms that we do have today will not introduce Lagrangian multipliers. Instead, they will directly try to find out the value and B, optimal values for W and B, without introducing Lagrangian multipliers. So in primal formulation, our goal is to directly find out W and B. In dual formulation, we solve for alpha I using indirectly determine the support vectors and using them to indirectly determine the support vectors and obtain the final hyperplane parameters. So we solve for alpha in dual formulation, we solve for alpha A. In primal formulation, we directly solve for W and B using some specialized algorithms, and they don't introduce Lagrangian multipliers. Okay. So that's how we solve this optimization problems. In dual form, we solve for alpha A, and from alpha A, we indirectly determine the support vectors in the hyperplane. That means alpha A, using alpha A, we determine W, and from W, we determine B. Okay, but in primal form, we directly solve for W and B to form the hyperplane. So we often solve the dual problem directly, since it is computationally more efficient. Okay, dual form is more efficient, even though if you look at this is order of n square. We have n number of multiplications, right? So the training of SVM is a little slow. Okay, it takes lots of time to actually train this model on the training dataset, because order of n square, if you know big O notations, big O notations, order of n square can be understood. That basically means, like, if you write two for loops inside one another, I is equal to 1, I less than 100, I plus plus. Inside this, if you are trying to write in another loop for j is equal to 1, j less than or equal to 100, j plus plus. So this for loop, you iterate n times. J less than or equal to 1, I less than or equal to 1. So inside for loop, you iterate n times. Again, for the outer loop, you iterate again n into n times. right? So that is the reason you are getting it as order of n square. Here also you're doing the same thing. What you're doing, you're iterating through I is equal to 1 to n for one of them, and again multiplying with every term with the whole term. So this becomes n square problem. So training of SVM is little slow. Okay, so that is what dual formulation and primal formulation for SVM is, and we have derived so many stuff. I mean, we understood so many factors of SVM. The main important things are the alpha I is 0 for non-support vectors, and alpha I is greater than 0 for support vectors. So W is a linear combination of all the input points, but after understanding that alpha is equal to 0 for non-support vectors, we can say that W is determined only using the support vectors. That means hyperplane is determined only by the support vectors, not every point in the data set that is given. It will be determined only for the support vectors. What are the support vectors? Support vectors are the edge points of the clusters, or the edge node of a um, particular group of points, or a particular class. Okay. So we often solve dual formulation for computational efficiency. That is what you have to understand. Okay. And now you know hard margin SVM. Okay. We don't allow misclassifications in hard margin SVM, right? But now, if you have an outlier, like if you have something like this, if you have a point, something like this, that means if you have an outlier and if you have a hard margin, the constraint that we have taken is not satisfying, right? You have to carefully understand. This is the last complex topic, I think. Other than that, it should be very easy. Okay, it's easy. This is, I think, this is a little bit important to understand. It's easy for you to understand as well. Don't Let's focus on a bit for next 30 minutes, so you'll be done with most of the stuff in this as well. Okay, now. Now, mm, Now, let's understand this carefully. So we have this outlier, right? Now we came up with this constraint for hard margin SVMs. But for this outlier, this is not satisfying, because let's take the class of these red dots as +1 and take the class of these dots as -1. Okay. And now let's suppose W xi into B for this is, let's suppose that distance, this wi into xi plus b is 20, because this is on the other side of hyperplane. This is h of x, and for every point above this, h of x is greater than 0. And for this point, let's suppose for this point, h of x is 20. Okay, but this the class of this point is -1. -1 into 20 is becoming -20, and this is not greater than 1. So the constraints are getting failed if we have some outliers, or if we have some points on the wrong side. Okay, so this constraints is no more valid for if we have misclassifications in the data set. Now for that, what we are doing is we are changing the constraint to something like this. Okay, we are introducing something called as slack variable. This is called as slack variable. What is this called? This is called as slack variable. This is called as slack variable. Now we are modifying the constraint to something like this. Earlier the constraint is this. Now we have modified this and added minus sigma I. Okay. So this is called as slack variable. Now let's see if this new constraint is solving the problem of this particular outliers. Okay. And there is another thing, sigma I is always greater than or equal to 0. Slack is always greater than or equal to 0. How do we calculate the slack? I'll show you how do we calculate the slack. Okay. And then we will come back to this particular screen. Now let's understand the slack variable measures how much a point violates the margin constraint. What is the margin constraint? Margin constraint is yi w transpose xi is always greater than or equal to 1. Okay. Now before doing this, I think I just have to, okay, this is fine. Now let's take this thing, yi w transpose xi plus yi w transpose xi plus, oh, how can I go do this? Okay, let's understand this carefully. Slack, what does the slack measures is that we introduced slack in the constraint variable for these kind of problems. In these kind of problems, when we have a point on the wrong side, we are not, this constants are not getting satisfied. Okay, instead of greater than or equal to 1, this goes to less than or equal to 1. Now we want to make sure even those cases are being valid with the constraints. So we introduce slack variable. How this slack variable is actively solving this problem is something you have to understand here. So how much point violates the margin constraint? Okay, sigma I measures how much a point violates the margin constraint. So this is violating the margin constraint. Similarly, this violates the margin constraint, this violates the margin constraint, because here yi into h of x is less than 0, but you have to get greater than 0. Here it is greater than 0, but you should get less than 0, right? Because if you take this class as 1 and this class as -1, and for every point below the hyperplane h of x is equal to less than 0, and here h of x is greater than 0, right? But for this point h of x is greater than 0, but class is -1. So -1 into h of x positive will become -1. But what is the constant that we have added? We have added constant as yi into h of w yi w xi plus p should be greater than 0, but for this point it is less than 0. Similarly, for this point h of x is less than 0 and class is +1. +1, h of x is less than 0, so yi into h of x is becoming negative. So these points are also getting failed with the constraint. So to solve that, and we added a constant, we add slack variable to the constraint problem, which is greater than or equal to 1 is the constraint, minus sigma is something what we added. This sigma is nothing but slack variable. How do we calculate slack variable? Slack variable is nothing but maximum of y 1 minus yi w transpose xi comma 0 or 0. Whichever is maximum, then we take that particular value. Okay. Now let's take this case. Okay, let's again go back, erase everything, and come back to a fresh screen. Now we understood slack should be calculated like this, which is maximum of 1 minus yi w transpose xi or 0. Okay, now tell me this thing. Okay, this red is +1 class. Okay, this gray, this is -1 class. These points, right, these are misclassified, they are on the wrong sides. Okay, now let's calculate the distance of a point from h of x is nothing but distance of a point, right? That is yi w transpose yi into w transpose xi plus p. For now I'm just ignoring this, I'm considering b as 0 for now. Let's just take yi w transpose xi is the distance, right? By mod w will be there, just ignore that as well. That's a scalar value, and it applies for every point. So just ignore that as well. Now let's carefully understand for the right points. For this point, what is the value of h of x? For this point, let's suppose this is the distance. What is the distance? What is h of x for that point? H of x is W transpose into xi is the distance. So it would be something h of x, we know h of x is greater than 0 for these points. H of x is greater than 0. And for the hyperplane below, for the points below hyperplane, h of x is less than 0. And for the hyperplane, h of x is equal to 0, right? So we know this. So now we are talking about this point. We are talking about this point. I'll mark this as 1. We are talking about point 1. Okay. For point 1, h of x we know greater than 0. And the class of this is 1. So yi into h of x, which is w transpose x, is greater than 0, right? Right or not? Yi into h of x is greater than 0, right or not? So this,
Yes.
you, if you remember, this is h of x is equal to 1. We made the distance of this margin as 1 in SVM. This also 1. So h of x is equal to minus 1 here. H of x is equal to 1 here. So any point above this will have h of x greater than 1. Right? This is 1. And if this distance is 1, and if there is other point beyond this, the distance of them will be, h of x will be greater than 1. And for every point beyond this, have h of x, less than minus 1, because this is 1. And beyond this, we'll have h of x minus 1. Agreed to that? H of x is equal to 0. We made the support vector lines as h of x is equal to and h of x is equal to minus 1. We made that to 1. Now, any point beyond that will have h of x greater than 1, and any point beyond this margin have h of x less than 1. Now, you say for point 1, h of x is greater than, not greater than 0, it is even greater than 1. Okay. For point beyond this, h of x is greater than 1. For point 1, I'm talking about. So, ya into h of x is greater than 1. H of x is nothing but, when we consider, for this whole stuff, we are considering b as 0. Even if you have b, you just add w transpose xi plus b. Okay. So this becomes ya into w transpose x plus b is greater than 1. When we consider b as 0, so this becomes ya into w transpose x is greater than 1. Okay. Now calculate the slack for this. The slack says maximum of 1 minus ya transpose x. Ya transpose xi is greater than 1. That means y, this is greater than 1. That means 1 minus greater than 1 will become negative value. Maximum of, so sigma I becomes maximum of some negative value. Let's call this as minus 2 comma 0. So the slack for this point will become 0, right? For point 1, which is rightly classified and it is on the right side. Okay. If you take any point, for this point also h of x is greater than 1. Ya into h of x will be greater than 1. So this becomes negative. So maximum of negative and 0 is 0. This is rightly classified. For this point also, ya into h of x is greater than 1. For this point also, ya into h of x is greater than 1. Now take the point which is wrongly classified. Let's take the point 2 now and do the calculations. For point 2, okay, for point 2, we are doing the stuff. For point 2, h of x is greater than 1, right? For point 2, h of x is greater than 1. Awesome. Because any point above this particular line parallel to the hyperplane will have h of x greater than 1. But yi for that particular class is minus 1, because red dots have class plus 1 and these gray squares will have class minus 1. Now let's say yi into h of x. H of x is nothing but w transpose xi, where when b is equal to 0. Ya into h of xi will become less than minus 1, right? Less than minus 1 or not, because h of x into h of x is greater than 1, ya is minus 1. So that becomes less than. Multiply these two, 1 minus 1, 1 into minus 1 will become minus 1. Greater than will become negative, less than, because we have minus multiplied on the other side. So ya into h of xi will become negative value. So now if you calculate the slack, maximum of 1 minus YAW transpose XI for the wrongly classified point 2 will become negative. Let's call this as minus 2, comma 0. So this becomes maximum of 1 minus of minus plus 3 comma 0. So slack for this is becoming negative, is becoming positive. Okay. So two things you have to understand. Slack for misclassified point is greater than 0. Slack for rightly classified point is 0. Slack for rightly classified point is 0. Slack for misclassified point is 3. Let's suppose this is going far from the hyperplane. Now let's suppose this is not for this point slack is equal to 3. If it is going far from this point, what happens? H of x will further increase. Let's suppose for this case, h of x we consider it as 2. Okay, for this case, h of x is considered as 2. For this case, h of x will become, let's suppose, 5. So this becomes 5. So 1 minus of minus 5 will become 6. Slack will become 6. Okay. As the points move much further away from this hyperplane, the slack value is increasing for the misclassified points. But for rightly classified points, that will always be become 0 because let's suppose for this point, the distance is taken as 2. Okay. For this point, with the distance is taken as 2. If we have another red dot here, the distance is 5. So this distance is 5. 1 into 5 is positive. So 1 minus of 5 will become minus 4. Maximum of minus 4 comma 0 will again become 0. Okay. Understood. So this is becoming negative. Even if it is increasing, this negative value is increasing from minus 4, minus 3. I mean, this negative value will increase minus 4, minus 5, minus 10, minus 20. It doesn't matter if it is minus infinity because we are taking the maximum of negative value and 0 will always be 0. But if this value is increasing, what happens? This is becoming 3, 4, 5, 6, 100. So this become will be slack value because this is wrongly classified. So this become minus and minus is becoming positive. So what you have to understand is for the rightly classified points, slack will always be 0. But for wrongly classified points, the slack is increasing drastically based on its distance from the hyperplane. Okay, so that is case 1. Is this clear? Hello.
Yeah.
Now let's talk about the point available here. Okay, now if the red dot is available in between these two lines, okay, how does that value looks like is something that you have to understand. Now if the red dot is in between these two, okay, let me draw that. If the red dot is here instead of somewhere, if the red dot is here, still if the red dot is here and gray dot is here, and if this is a gray circle, let's calculate the slack values again for these 2 points. Okay, now it's good to come back to this color again. Now let's understand this. We understood this case, or we have analyzed all these points and we found out that slack value for the misclassified will always be greater than 0. For the rightly classified, it is 0. Now now again take this point, this gray point. Let's call this as third point. Now we're talking about third point. For the third point, h of x is less than 1, but it is greater than 0. Right, this distance is greater than 0, but it is less than 1 because this is 1 and anything below this will have less than 1. So h of x is this. Y of I is equal to minus 1. Y of I equal to minus 1. This is wrongly classified on the wrong side. So h of yi into h of x will be in between. Yi into h of x will be what it will be, less than minus 1, right or not? Y into h of x less than 0 and greater than 1. Uh, Less than 1 and greater than 0, right? So that is how it looks like. Edge. So it's as simple as this. So when we are multiplying y of x1, this greater than symbol will become less than, and 1 becomes this side, and the other 1 becomes other side. So h of now ya into h of x will be in between 0 and 1. Okay. So now what slack becomes? Slack becomes 1 minus, this is somewhere in between 0 and 1, that becomes uh, what does that will become? Ya into h of xi will be a negative value, right? Let's take an example like this. Let's say the distance is 0.5. This is simple to understand for you, and ya equal to -1. Okay, so now slack becomes -1 into 0.5 will become minus 0.5 comma 0. So slack becomes 1.5. Okay, for zero point 0.4, if you say for 0.4, for 0.4, what is this becomes? H of x is equal to 0.5 for that, but y of I is +1 for this. So slack becomes maximum of 1 minus, this becomes positive value, which is 0.5 comma 0. So maximum of 0.5 comma 0, which is 0.5. Okay, so for rightly classified point, slack is 0.5, but wrongly classified within margin, it is 1.5. Okay, so that's how you calculate the slack variables for different points. Okay, slack is nothing but 1 minus ya w transpose xi comma 0. Okay, this is how you calculate the slack, and we have calculated slack for different points. Now understand, for a good point, what is good? Good means which is on the other side of, which is on the right side with the right label. For these points, for the point ones, slack is always 0. Bad but within margin. Okay, for the points, this is bad. This is not on the other side of the margin. This is misclassified. Okay, but it is on the right side of the hyperplane. This is misclassified. That means we allowed misclassifications here. I mean, it is within margin. Okay, but on the right side of the hyperplane, it is still on this side. So for these points, slack will be 0 less than or equal to 1. For these points, this is 2, this 2, this one, this one, these are all misclassified. This is on the wrong sides of the hyperplane. This technically has to be on this side. This red dot has to be on this side only, but it has to be here for getting this to 0. But if it is within this margin, that will have slack value less than 0 or equal to that will have slack value in between 0 and 1. Okay, for these misclassifications, all these points has to be on this side. So the slack value, as they are on the other side, the slack value of them is greater than 1. For all these points, slack is greater than 1. Let's suppose if you have a gray point here, what the value of that will be? What the slack value for this, if you have a gray point here? The slack value for the, if you have a gray point here, the slack value for that will be in between 0 and 1, because it is on the right side but within margin. If you have a red circle here, what will be the slack value for that? Greater than 1, because it is on the, it is within margin but on the wrong side. Okay, for this, what is the slack value for this red point? For this gray,
0.
0, right? So the takeaway here is that if the point is on the right side and outside of the margin, the slack value will be equal to 0. If the point is on right side but within the margin, slack value will be in between 0 and 1. If it is completely on the wrong side, slack value will always be greater than 1. Now going back to this condition, now you know how to calculate the slack variable, right? Now let's see if the constraint is satisfied for this or not. Okay. Now take this point. For this point, slack is 0, so the constraint is satisfied. If you take this point, what is the slack value for this? Slack value for this is greater than 1, right? Slack for this is greater than 1 because this is on the wrong side. So now what a constraint will become? Yi into w of x, yi into w of x plus b is greater than or equal to 1 minus slack value is greater than 1. That becomes, let's suppose this is greater than 1 means, let's suppose if it is 5, yi wx plus b is greater than or equal to minus 4, right? So now what this is becoming negative, right? So this is becoming negative now. So instead of positive 1, we are getting a negative constraint. So that is satisfying, right? So this is always will be greater than or equal to minus 4. Understood? So this value is not getting reset. So as this is 1, this is when we don't introduce slack value, what is this becoming? This becoming minus 20, right? If you say this is minus 20, okay. So this minus 20 is not greater than 1. But now what is our constraint changing down to for the same point? Now if you introduce slack variable, now what is that slack? Now the slack is becoming what? Slack is becoming minus 20 now, right? For this point, slack is calculated as 1 minus yi w transpose xi, and this we are saying as minus 20. 1 minus of minus 20 will become 20. So slack will become 21. Slack will become 21. So the constraint for this point is turning down to yi w into w of x bar plus b is greater than or equal to 1 minus slack, which is 21. So we say this is greater than or equal to minus 20. So this is getting minus 20. So the constraint is satisfied for this point as well once we introduce the slack variable, right? So the constraint is getting changed based upon the point on which side it is there. So the constraint is getting satisfied for each and every point. Understood? So now the new constraint became this one. By introducing the slack variable, we are satisfying the constraint for every point. Whereas in this case, we are not getting, this constraint is not satisfied every point. But when we introduce the slack variable into the constraints, so the constraints are getting generalized, or this constraint is getting valid for every point, even if it is misclassified. So that is how you calculate the slack, and that is how the new constraint problem got changed. Now, what is our new function? Earlier, the objective is to minimize w square by 2 in the primal problem with the constraints of yi w of x bar plus b is greater than or equal to 1. This is the constraint problem earlier. Now, this constraint problem got changed to this new optimization problem. That is what it says. Now, we want to maximize the margin, right? And also minimize this misclassification, right? We want to maximize the margin, but we want to minimize misclassifications. Okay, that is what it actually means is you don't want so many points to be misclassified. Let's suppose this is the example that we have talking about, right? So let me go back to this example and show you. We are going forward, back. Keep. Where is this? We were talking about what is the best margin, right? What is the best margin is what we were talking about. Okay. If you go back here, earlier our objective is what? Our objective is to maximize the margin without misclassifications in a hard margin SVM. In hard margin SVM, what we are trying to do, we are trying to maximize the margin. Okay. I was also talking about a case. I don't know if that diagram is there with me more or not. I was also talking about a case with you, right? So I don't know if I have, let me quickly draw the diagram and show you. In one of the cases, we are trying to maximize the margin. Maximize the margin in the sense there can be many margins, right? So if I have points like this, if I have points like this, and I have points like this can be one of my margins. This can also be a margin, right? This can also be a margin, right? There can be a number of possible. So if the lines passing these through support vectors, we have this margin. If we have this passing through this support vector, we have this margin. The width of this margin is less than this margin. So our primary goal is to maximize this margin so that the hyperplane will pass through the center of those two lines, or those two margins. So that is our primary objective. Now, here we didn't allow misclassifications, but if we don't allow misclassifications, what is happening? We are not able to achieve the right results in where we have outliers, or the data where we have outliers basically. So if you consider this particular case, where is that? If you consider this particular case, it is good to misclassify this point. Okay, it is good to misclassify this point so that you're doing the right classification for the test data set. If you're getting a new point here, if you're getting a new point here, without the misclassification, we are treating that as red dot. That belongs to red class, right? If you don't misclassify, and if you consider these as support vectors and deriving the margin here, if your new test point is coming down, you're saying that as red dot. But if you allow misclassifications, and if you get a new test point, even though if you misclassify it for the test point, as this is close to these green dots, it is good to classify this as green point, right? So it's good to allow misclassifications, but how many misclassifications that you have to do, right? That is the question. So here you have misclassified one point, and here you have misclassified so many points, which is giving good accuracy. Is this giving good accuracy, or is this giving good accuracy? How many points that you have to misclassify is something that you have to decide, right? So that is decided using this equation. If you go back here, this is the trade-off between those two things. So if you look at this, the new optimization problem is minimizing the margin and minimizing the slack. Okay, maximizing the margin and minimizing the slack. When the slack is minimized, what happens? All the points will be rightly classified, right? Let's take two cases again for you to better understand. If all the points are rightly classified, what is the slack? Let's suppose if you have all the points like this. So if you take the same example, if all the dots, if all the circles are on this side, and if all the, you know, if all the squares are on this side, what is the slack for this case? What is the slack for this case? Slack is 0 for this case, because for every point slack is equal to 0, because they're on the right side. Okay, so if you take the other case, something like this, the reds are here, the blacks are here, and if you have one black point here, and let's go back to the red case. So if you have red dots here, something like this, and you have some red dot here. So slack for this is called as, let's say it is 10, because slack of this is greater than this point, because you have some misclassifieds, and for this slack is greater than 1, and for this also slack is greater than 1. So it sums down to slack is equal to 10. Okay, if you have so many misclassifications, let's suppose I have so many red dots on this side, and red dots here on this side, and if I have so many black dots on the right side and also on the wrong side. Okay, so many red dots and black dots on both sides. Slack of this is something like 1000, which is much more than this one. So what is this coming down to? When there are more misclassifications, when more misclassifications are allowed, slack is increasing. But we don't want to um, get more slack. What we want to achieve? We want to achieve good accuracy with minimizing the slack. We want to minimize this. Okay. We want to minimize the slack and maximize the margin. Okay. So we want to maximize the margin and minimize the slack. When we minimize the slack, the number of misclassifications that we are allowing is decreasing. Okay. Now to trade off, what has to be given importance, whether you want to give importance to maximizing the margin or minimizing the slack, to which you want to give the importance. So when you minimize the slack, what happens? When you're trying to minimize the slack, margin will become less. Okay. When you maximize the margin, what happens? Slack will become, when you maximize the margin, what happens? Slack will become increasing, right? Slack will become increase. So when you maximize the margin, so many points will come within this range. So margin will actually margin will increase, but slack will also increase, right? So this is the actual margin where slack is equal to 0. In this case, slack is equal to 0. Now let's increase the margin. What happens? So for these points, slack will be in between 0 to 1, right? So slack will be greater for this case. When margin increasing, slack is also increasing. So what is the trade-off? Whether you want to get the maximum value for margin or slack. So for that trade-off, you're introducing this value called as C. This C decides what is the importance that we need to give for the slack and what is important that we need to give for the margin. Okay. So this is the margin parameter and this is the slack parameter. You want to maximize the margin and minimize the slack. So this is also minimization, but margin is maximizing the margin is nothing but maximizing 1 by W. That turns down to minimizing W square by 2. Okay. So for this total will be a minimization problem, but this is also minimizing. We also want to minimize the slack. So this total problem will be a minimization problem. But when in terms of margin thing, you want to maximize this. Minimizing this is nothing but maximizing margin. Minimizing this is nothing but minimizing slack. Okay. Now let's understand the value of C and how this actually decides the importance for this and this. That's the second thing that you have to understand. Okay. Now, when C is more, what is happening? When C is more, look at this. When smaller C emphasizes the importance of sigma. Okay. When sigma is small, when C is small, it emphasizes the importance of slack. That when C is small, slack will be given more importance. And larger C diminishes the importance of sigma. When C is large, the importance for slack will be diminished. Okay, let's understand this with some example. Okay, the statement says when C is small, more emphasis will be given for slack. When C is large, uh, less emphasis will be given for the. Did I say it in the other way? A smaller C emphasizes the importance of sigma. When C is small, more importance for sigma. When C is large, less importance for sigma. Okay, that is what it is. When smaller C emphasizes the importance for sigma and larger C diminishes the importance for sigma. Okay, how it actually will do that? Okay, let's understand this with an example. So it is saying that let's take this example again. 1 by 2 W square plus C into slack. Okay, so this is our equation, sum of slacks. What is this? This is a minimization problem. We want to minimize this whole term. Okay. Now, when I take C is small, when I take C is equal to small 0.0003, multiplied by, let's take some slack value of 100 and 100. Okay. The margin is 100 and slack value is 100. Let's take the same value so that you will understand what is the importance of C. Now, if I come down to this calculations, this is 100 plus 0.003 into 100 will become 0.3, right? Right or not? 0.003 into 100 will become 0.3. Now we want to minimize this whole value. Then emphasize the importance of. Let me just I think look at this. So when C is small, the margin is 100 and slack is become 0.3. So when you're trying to minimize 100 and 0.3, what you're trying to do, you're trying to minimize this, right? When you're trying to minimize, you will try to minimize this. That means you are trying to maximize the margin. More importance is given to maximizing the margin because this is anyway a small value. 100 plus 0.3. So even if you try to minimize this here, it becomes 0.2, 0.1. If you bring this down by scale of um, 10 times or somewhere around 10 times, so what happens, it just comes down to 0.03, right? It which the total value will is not changing it drastically. If you scale, if you minimize this by 10 times, it becomes 0.03, but the total value is still becoming 100.0.03. Total value is still 100.0.03, right? But if you minimize, in this case, if you minimize this by 10 times, what that is becoming down to 10 plus 0.3, which is becoming 10.3. So as C is low, it will concentrate more on margin. Okay, minimizing this is nothing but maximizing the margin. If you look at C is equal to 0.03, the margin is too high. There is no emphasis given to, I mean, it's free to there is no importance given to reduce the slack value. That means more importance is given to maximizing the margin. So more misclassifications. Now if you look at this particular case, if you look at this particular case, 100 plus 100 into 100. Now this value is too large, right? Now instead of minimizing this, it tries to minimize this particular value. That means it tries to reduce the slack. Reduce the slack means margin, there is less emphasis given on margin. So it tries to drastically reduce the slack. Reduce the slack means margin will become less. Okay, so when does slack will reduce? When everything is classified on the right side. When do everything will get classified on the right side? So when the margin is too low. You have seen one case, right, where the margin is too low. In this case, margin is too low. That means everything is classified on the right side. So more emphasis is given on right. It will not allow more misclassifications when C is large. When C is large, it will not allow more misclassifications. Less when larger C, less tolerance for misclassified points because it tries to minimize the slack when C is more. When that means misclassified point should be less. Okay, just ignore this. Ignore this statement. You have to understand this. When C is large, it it will not allow more misclassifications. It tries to reduce the slack to a greater value. Smaller margins and more reliance on correct classifications. So when C is large, it tries to minimize this when compared to this, right? When it is trying to minimize this, that means it is trying to minimize the slack. Minimizing the slack is nothing but rightly classifying the data. When C is infinity, it's equal to hard margin classifier. Okay, when C is infinity here, it is nothing but hard margin classifier. It will not allow any misclassification in the data sets. Okay, when C is less, more emphasis given to, you are free to misclassify the points, but you have to get the more margin. More emphasis is given to minimize this. That means more margins. Okay, There is no confusion. When C is large, when C is large, here C is large, here C is less. When C is large, this value is getting large. So minimizing this value is nothing but minimizing this, not minimizing. Even if you're minimizing this, the overall value will not be greatly impacted. If you have seen this example, right? If you decrease this by 10 times, this is coming down to 100.0.03. But if you decrease this by 10 times, it is coming down to 10.3. So more importance should be on this margin. So margin will be high in this case. Minimizing this is nothing but maximizing the margin. So when C is equal to 0.03, you see more margin here. But here in this case, when C is greater, it will reduce try to minimize this, means minimizing the slack. Minimizing the slack means points to be should not be classified in more points should not be misclassified. So you will see less margins. When you don't want to allow more misclassification, the margins will be anyways smaller. That is the difference between larger and smaller C values. Okay. Now, what does the primal formulation had become now? Primal formulation had become for soft margin SVMs where we allow misclassifications. We are introducing a slack variable. Slack will always be greater than or equal to 0. That we already have seen with an example. And you got two constants. The first constant is this yi, w transpose xi plus p is greater than or equal to 1 minus sigma I. So this constant is something that we have discussed here for the soft margin SVMs. For hard margin SVMs, you don't have this slack variables. Okay, that is the only difference. And slack will also be greater than or equal to 0. Where 1 by 2 w square is a regularization term, helps to maximize the margin. C greater than 0 is a regularization parameter that balances the trade-off between maximizing the margin and minimizing the classification, controlled by the slack variable. So C, okay, C is the parameter that actually decides the importance of slack variable. When C is large, um, more importance will be given to minimizing the slack. When C is less, more importance will be given to maximizing the margin, that we already have seen. Now to solve this Lagrangian equation, you have to actually introduce two Lagrangian multipliers. As you have two constants, you are introducing two Lagrangian multipliers here. One is this is the equation for us. Okay, this is the primal equation. This is the soft margin equation, and these are constants alpha I w transpose xi minus 1 plus sigma. I'm taking this to the other side, so this becomes greater than or equal to 0. For a slack variable, we are introducing a second Lagrangian multiplier. We introduce two Lagrangian multipliers. Okay, two Lagrangian multipliers are introduced, and now this is the new Lagrangian equation for the optimization problem of soft margin SVM. Now again solve this for again derive this with respect to W. This is the expansion form. And if you take this, and again KKT conditions are here. KKT conditions, what they say, the constraints are equal to 0, right? The constraints are equal to 0 and Lagrangian multipliers are always greater than or equal to 0. Okay, we have three. You have to take the Lagrangian derivatives of every variable. That is the first condition. Second condition says um, um, Lagrangian multiplier multiplied with the constant should be equal to zeros. The third condition says the constants are less than 0. Constants are less than 0. And third says all the Lagrangian multipliers are greater than or equal to 0. That are the four, KKT conditions. Now, if you derive with this with respect to W, what that will be, what that will become? It's again, when you derive this with W, this becomes 1 by 2 into 2W. It's simple. 1 by 2 into dW. Again, there is no W here. It becomes 0. Here, there is a W in this term. So that becomes minus sigma I is equal to 1 to N alpha I yi xi. So there is no W term here. There is no W term here. So this becomes equal to 0. 2 and 2 will get cancelled. So W will be equal to minus 1. W equal to minus sigma equal to 1 alpha yi and xi. If you do with respect to B again, there is only B here. Alpha into yi will become equal to 0. So that becomes 0. And if you do with respect to sigma I, okay, when you derive this with respect to sigma I, there is no sigma I here. It becomes 0. There is sigma I here. So that becomes C. Where is sigma I? Here there is a sigma I. So what it is multiplying with alpha I. So minus alpha I. Sigma I is equal to 1 to N alpha I. And here is sigma I minus beta I. Okay. So this is something. So now, you know, Now C is equal to alpha I plus beta I. Okay. Now alpha I can be written as C minus beta I. Okay. You know, from these two conditions, alpha is greater than or equal to 0, you know, and beta is greater than or equal to 0, you know. So now alpha is equal to, there is another condition, C minus beta I, right? So now alpha I values will fall between 0 less than or equal to alpha I less than or equal to C, because the minimum value of C is B, right? When beta is equal to 0, alpha is equal to C. So the maximum value possible for alpha is equal to C, and beta is increasing. Let's beta is equal to 1. This C value will become C minus 1, C minus 2, something like that. So now the only difference between hard margin SVM and soft margin SVM is, in hard margin SVM, alpha I can take any values. But in soft margin SVM, alpha I can take only values between 0 and C. What is the C? C is the tuning parameter here. That decides the importance between the margin and the C. This is the regularization parameter. Okay, so this C decides the importance of margin and C. So now alpha value will be within between 0 and 0 and C. Now we are trying to find out the value of alpha I, right? So now when you get any alpha, when you're trying to find out the optimization problems of, when you're trying to find out the optimal value of alpha I, you don't need to consider infinite values for I. You consider only the values within this range, so that optimization problem will become little faster. Okay, solving alpha I would be little easy, because when you get more than C value, you fix that to C. Okay, you fix that back to C. That is how you actually improve the efficiency. As you know, the value of alpha is just in between these two values. So the constant 0 alpha less than C ensures that alpha lies within the specific range determined by the regularization parameter C. The equality constraint enforces that the support vector points for alpha balances between the two classes. This again we have seen. The alpha values of the positive class will be cancel the alpha value of the negative class. So only the only difference between the hard margin SVM and the soft margin SVM is that soft margin SVM alpha values will be just in between 0 and C. Okay. When you actually solve the optimization problems. Okay. Again, if you take this equation again, now if you, this is the primal formulation for the soft margin SVM, right? Now if you talk about the hard margin SVM, hard margin SVM dual formulation, it is simple, you can easily understand that. So again, dual formulation, what are the things that you know? W is equal to sigma is equal to 1 to n alpha I yi xi, right? Replace the same thing. And also, you know, alpha I by a is equal to 0. Alpha I by a equal to 0. So this term will become 0. So this term will become equal to 0. Now let's expand this and see what, no, how does this comes down to. This becomes 1 by 2 w square plus c sigma I is equal to 1 to n sigma I minus sigma I is equal to 1 to n alpha I yi w transpose xi plus, sorry, this becomes minus sigma I is equal to 1 to n alpha I yi b, right, minus sigma I is equal to 1 to n alpha I yi. This becomes plus, right? Minus I minus will become plus, and the lastly it becomes minus sigma I is equal to 1 to n alpha I yi sigma I for the last term. Yi will not be there, I guess, for this. Yi will not be there for this. For this also it is just minus I, because alpha I will be multiplied only with this, and here also yi will not be there. Minus sigma I yi into 0 is fine. Minus sigma I is equal to 1 to n beta I sigma I. So now this becomes 1 by 2 w square uh, 1 by 2 w square plus c sigma I is equal to 1 to n sigma I minus this becomes W transpose again. Sigma I is equal to 1 to n alpha I yi xi. Okay, so this term will become 0 because alpha into yi is 0, plus sigma I is equal to 1 to n alpha I minus sigma I is equal to 1 to n alpha I sigma I minus sigma I is equal to 1 to n beta I sigma I. Okay, so now this turns down to 1 by 2 W square. So this becomes minus W transpose into W, which is become W square, plus keep this aside, sigma I is equal to 1 to n alpha I. Now if you take these three terms, that becomes plus C sigma I is equal to 1 to n sigma I minus sigma I is equal to 1 to n alpha I sigma I minus sigma I is equal to 1 to n beta I sigma I. Okay, so let's take that sigma I outside. Sigma I is equal to 1 to n sigma I. Thus becomes C minus alpha I minus beta I. Okay, C minus alpha I minus beta I. C minus alpha I minus beta I is equal to 0. Okay, so C minus alpha I minus beta I is equal to 0. So this whole term should goes to 0. Now the only terms that are are these three terms, right? So now if you rewrite those three terms, that comes down to this way. So that is sigma I is equal to 1 to n alpha I minus W transpose into W is become W square. W square by 2 minus W square is minus 1 by 2 W square. W square can be written as summation of these things. We already have seen this. So now what is changing between the primal and second? The dual formulation didn't got changed. The only thing that got changed is the value of alpha is just in between 0 and C. That is the only thing that got changed. Earlier, alpha is greater than 0 in the dual formulation of primal equation, right? So this is the dual formulation of primal equation. Here alpha is greater than or equal to 0 for every I. But here in the soft margin SVM, alpha value will be just in between 0 alpha and C, 0 and C. Okay, so that is the only difference between dual formulation and the dual formulation software as soft margin SVM and what is that, primal formulation software. Um, primal formulation of hard margin SVM. Okay, now if you there is a simple trick for calculating the value of p. Okay, there is a simple trick to calculate the value of p. So I'll tell you that for p, what you're trying to do again, wxs h of x. You know h of x is equal to wx plus p, right? Mm. Now what you're trying to find, how do you trying to find out ws into xs? H of x minus wx into h of x. This is what you're trying to do. Right, this is equal to 0, this is equal to 1. uh, you're trying to find out b by taking the support vector, when the support vector is xs, and you know w into xs plus b is equal to 1. So you're trying to find out b by 1 minus w into xs. This is how you're trying to find out the b value, right? So I have shown you calculating the b value in one of the slides. Ys. So this ys is the class of that. So this is ys minus wx minus. So this is the class here. One is the class. So this becomes ys. That is how you calculate the value of p. But you don't need to actually do all these calculations. To minimize this effort, what we can just do is we can just do this. So now I'll extend my weight vector in such a way that this becomes w1, w2, so on wn, comma b. Okay, Now x will become x1, x2, so on, xn, comma 1. Once I extend this way, you know the hyperplane equation h of x is equal to w transpose x plus b. Here w is nothing but from w1 to w2, so on, wn. Okay, and x is nothing but x1 to xn, x1 comma x2 comma so on xn. So this is the initial formulation that we have done. Now we have, this is the n dimensional vector. Now I made that n dimensional vector to n plus 1 dimensional vector, and in this vector, if I found out b, the last uh, dimension of w is the value of p. Now if I multiply these two things, what will happen? It becomes w1x1 plus w2. If I take the dot product of w into h, now h can be written as w dot product of x in n plus 1 dimensions, right? Here h of x is equal to w transpose x plus p in n dimensions. In n plus 1 dimensions, w and x is just the dot product of w and x. So this, if you take the dot product of these two things, it happens w2x2 plus w3x3 plus so on plus w1xn plus b, right? So now this is same as this one, right? If you take the dot product of these two, it comes down to w1x1 plus w2x2 plus so on w1xn plus last term is b. Last term is b. So these two are equal. Now I extended the vector from n to n plus 1 dimension, so I don't really need to do the additional calculations for b. So if you want to know the value of b, it is just the last dimension of the weight vector. So that's how you can simplify the calculations for b. Okay, just add 1 to your n-dimensional plane. Okay, so that is all about the primal formulation, dual formulation, and just make sure that you cannot actually, what to say, solve the value for alpha I or WB in primal formulation directly. They need softwares to actually solve those optimization problems. Okay, we have done all those derivations just to understand important facts about software. I mean, support vector machines. Okay. Now it's 146 for you, 148. So we need to just cover at least 5 different slides now. Okay. I'll just give a quick introduction to this so that we can cover this tomorrow. So now till this point, you are just trying to understand about linearly separable cases, right? So they can be separated linearly. But if you look at this, if you look at this data set, you cannot find out any line that actually separates these 2 points in a one dimensional, right? So even if you take any hyperplane, it cannot actually divide these 2 points. There is no hyperplane that actually divides these 2 points. How do we actually, how SVM achieves this kind of when it encounters these kind of data sets, how SVM deals in separating these two different classes is something that we are going to learn today. So most of the real world data would look like this, right? So they will not be linearly separable. That would not be so nice. The data would not be so nice to us so that we can just find out that simple hyperplane which separate these 2 points. You will get some mix match of different data points at different places. How do you achieve them? So to achieve the classification of these 2 points, we use something called as kernel. Okay, when we use kernel functions, we call them as kernel SVMs. Okay, we call them as kernel SVM, software soft margin support vector machines, kernel support vector machines. Okay, let's, how do we solve this is I'll show you a simple example. Like now if you consider the same data set in one dimension, you will not be able to separate those points. How do you separate them then? What you will do is you will extend them to two-dimensional spaces. Okay, from one dimension space you are extending that to two-dimension space. Okay, how you are extending that to two-dimension space? You're taking the second dimension as the square of the first dimension. Let's suppose the value of this point as 5. So if you square this, so this is the point in one dimensions. Okay, 5 is the weight of a the weight of a dosage. 5 mg of dosage is given for a particular patient, let's suppose. Now in when you want to change this from one dimension to two dimension, the second dimension would become 25. 5 comma 25 would be its second dimension. Now you're projecting the points from one dimension to a say two dimension space, and in the two dimension space you can get a line that separates both the points. Okay, so if you look at this particular data set, what is happening in one dimension space, you don't have any threshold that separates both the points. But when you extend these data points to two dimensional spaces where the second dimension is just the square of the first dimension, okay, where the second dimension is just the square of the first dimension, and in the two dimensional space you are able to successfully separate the 2 points. Okay, so that's how kernel SVMs will actually try to solve these kind of data sets. How they will try to classify these kinds of data sets. What they will do, they project the data points to higher dimensions, and in the higher dimensions they will try to find out the fitting hyperplane that separates both the data points. And now that the data are in two dimensions, we can draw a support vector classifier that separates the people who are cured and who are not cured. Let's suppose if this is the case of different patients given with some doses of a particular drug, and have seen that some patients are getting cured and some are not getting cured. If you understand this analogy, the patients who are given with less doses are not getting cured, who are given with very high doses are also not getting cured, who are given with only right dosages are only getting cured. Okay, so now even if you get a new patient, if you want to say, if you want, let's suppose if I got this new test data set now based on the earlier data set, this is the doses given for the new patient. Now let's say if he got cured or not, let's guess if he's cured or not. How do kernel SVMs will do this? Like, again, it transforms this point to two-dimensional space. Okay, it transforms this point to two-dimensional space, and as this point now is on the other side of the hyperplane, you say that as not cured. Let's suppose if you got a point here, square this point and transform this to two-dimensional space, and this is below this hyperplane, so you say this patient is cured. That is how kernel SVMs will actually solve the non-linear cases, non-separable cases. Okay, this is what I'm talking about. When you get a new data set here, we are transforming that to 2D space again. The 2D space is nothing but the square root. You find out the y dimension. Y dimension is nothing but the square root of this x dimension. So y, the whole point will become x comma x square. That is where you are able to find out the separating hyperplane. You transform this point. This point is on the other side of this hyperplane, so it is not cured. Okay, and if you get a point here, square this, it is falling on the other side of this hyperplane, so you say that patient has cured. That is how you classify the data on the test data set. So this is how kernel SVMs will do. The basic idea of kernels is that it transforms the data from the into higher dimensions and tries to find out the separating hyperplane. How many dimensions that it has to transfer? It has to be two dimensions. Into how many dimensions it has to project to find out that separating hyperplane is something that you will understand in the next few slides. Okay, let's close that in next 5 to 10 minutes. I won't take more time, but I want to cover the intuition behind the support vector machines. Okay. Okay, so that's how kernels will solve these nonlinear problems. So transforming the data to higher dimensions. Okay, so we already understood how to transform a data from one dimension to other dimension. Let's suppose when we transform the data into higher dimensional space, it may become linearly separable there. So in two dimension, right now, if you take this case, these are not separable. You don't have any line that can linearly separate these points. You don't have any plane or a line that actually separates these points, right? So when we transform these points to higher dimensions, we may find a line that can separate. A line in higher dimension is called as hyperplane. We already know that. we can create new features for each data point to separate the classes with a hyperplane in the higher dimensional space. Creating a new feature is nothing but in a data matrix, it is a column, right? So what is a feature in a data matrix? So this is like you're adding a new feature means you are adding a new dimension to it. So this is X, Y, Z. Now you don't know X, you don't know Z, right? You derive this new dimension from the existing points, and maybe in the higher dimension we may find a linearly separable line there or a hyperplane there. So that's the whole intention between transforming the data into higher dimensions and then finding an hyperplane over there. So if you take the same example here, by mapping the 2D data to 3D space, where Z is equal to the new dimension Z is derived from the two points X and Y, where Z is equal to X square plus S square, we create a third feature based on the original two. And now what actually happens here is that now if you actually try to look at this, this is how they actually look at this space. So right now you have these points. Let's if you just look at this animation, when we transform the points to higher dimensions, this is how you get a hyperplane. So all the points, all the dotted lines are coming down to uh, are coming below the plane, and all the points that are like your this is the 2D space, right? This is 2D space. You're moving them to 3D space now. So you're elevating the points, whereas z dimension is x square plus y square. So if you consider this as a room, all the points here are coming down, and all the points are moving further up in the space. So now this is the new dimension that we have got. So now if you got a hyperplane here, that is separating both the points. So that hyperplane in 3D is nothing but the a circle in the two-dimensional space. Okay, so that hyperplane in 3D is nothing but it's a circle in the 2D space. So that how did it become circle is nothing but um, what to say? So that hyperplane is is actually separating both the points, right? That actually means is that you're getting a new hyperplane there, right? That hyperplane is successfully able to separate both the points or both the classes. So in that case, if you bring that down to lower environment in 2D space, the it is forming a circle, right? So this is the circle which is separating both the points. So hyperplane in that higher dimension is just like circle in the lower dimensional space. So that is the reason of transforming to higher dimensions. Now, where is the where is the challenge here, right? How do we know how to construct the higher dimension? So is that x square plus y square, or x cube plus y cube, or xy, or x to the power of 10, or y? How do we know z? There are so many combinations available for z, right? So it's typically impossible. Now that's the next slide says what to take y-axis as. Earlier we have taken x square. Is that I mean, how do we know we have if it is 5 pi by 4 or root to the power of pi raised? How do we know it is doses cube? Or we cannot actually determine what formula we have to use that separates the points effectively, right? And we also know to how many dimensions we have to transform these points, right? So those are all challenges. We know in higher dimensions we can get a hyperplane, but how to transform this data? And in other words, how do we decide how do we transform the data? So that is what this diagram says. In order to make the mathematical simple, so support vectors usually do something called as kernel function. It's a trick that actually support vectors will do to systematically find the support vector classifiers in higher dimensions. So basically, it's a challenging stuff transforming the data to higher dimensions. And what should be the higher dimension? How do we derive the higher dimension from the existing dimensions? To how many dimensions we have to actually go ahead for be able for to be able to linearly separate the data. These are all challenging stuffs, right? So so to solve all that stuff, there is something called as kernel trick that came into existence. Okay, what that kernel trick basically says is that, so there are two challenges here. One is we cannot able to actually understand what should be the third dimension has to be. How does the third dimension to be derived from the existing dimension? And also transforming every point to higher dimension is also computationally very expensive. If you have billion points, you cannot transform all the points to higher dimensions and do that stuff. So there are few challenges. That is, calculating all the possible future mappings to higher dimensions would be computationally heavy and time consuming. You cannot transform all the points to higher dimensions. That is computationally expensive, and you cannot achieve such kind of computation. So kernel provides a clever shortcut. What it will do is it allowing us to perform these transformations without explicitly computing the higher dimension futures. Okay. So kernels are allowing us to perform those transformations without explicitly computing the higher dimensional spaces. Instead, kernel calculates the relation between the data points in original space and gives the same result as if we had the transformed them. So what kernels will do is kernels will just do the similarity calculation between the points in the same dimension in the original space. They will not actually do the transformation, but they mimic the transformation in the original dimensions only by calculating the similarity between the points in original dimensions, and based on those similarities they will come up with a hyperplane in the original space only. They will not go to the feature transformation. I mean, they will not transform the data points. To keep it simple, where we have started, we found out that for non-linearly separable cases, we have to transform the data to higher dimensions, and in the higher dimensions we were able to find out the hyperplane that separates the points effectively, right? But instead of that is we understood that transforming the points to higher dimensions is computationally inefficient, and we also found out that finding the higher dimensions, like what how do we derive the higher dimension from the existing dimension so that we will be able to actually separate the data points effectively using a hyperplane in the higher dimensions is unknown. The deriving how many dimensions is unknown, and transforming the points to higher dimensions is inefficient and computationally, and also there is wide possibilities of deriving the higher dimensions from the original dimensions, right? So instead what kernels will do is kernels will calculate the similarity between the points in the original space itself and mimics the transformation into higher dimension space and find out the hyperplanes in the original dimensions only. So let's understand this carefully. I said kernel is a function that takes 2 points in the original space and computes the similarity as if they were in the higher dimensional space. That means when we transform the points to higher dimensions and when we calculate the similarity between the points, transformed point similar calculating similarity would be same as calculating the similarity in the original dimension space using kernels. Okay, that is what I mean to say. Using kernels, we are mimicking the behavior of higher dimensional spaces similarity. Similarity is nothing but cosine similarity is one of the similarities, right? Cosine similarity is nothing but dot product of those 2 points divided by the modulus of those 2 points. Cos theta is nothing but a dot b by mod a mod b. So a dot b is one sort of similarity, right? A dot B is one sort of similarity. Calculating the dot product between these two vectors will give us the similarity. Now, I would I would just show you an example of how does this actually work. So let's suppose I have 2 points, 1, 2, and 2, comma 3. So these are my two-dimensional points. I transform these points to 3 dimensions in such a way that my first dimension is x1 square, second dimension is root 2 into x1 into x2, and the third dimension is x2 square. So now using these points, this is my new dimensional, three-dimensional space in which I was able to find out a hyperplane that is separating those 2 points. Let's suppose. Now I'm transforming these 1 and 2 into this higher dimensional space. So the calculation become 1 square, x1 square, root 2 into x1 and x2, 1 into 2, and x2 square. So my transformed point is 1, 2 root 2, and 4. And transformed point for 2 comma 3 is 4 6 root 2 into 9. And if I calculate the dot product between these 2 points, that is coming down to 64. Okay, 1 into 4, 2 root 2 into 6 root 2 into 4 into 9. So similarity of the transformed points in higher dimension is turned down to 64. Now what I'm saying, Here, what you have done, you have transformed the points and then calculated the similarity. If you have billion points, what you have to do, you have to transform all those billion points into higher dimensions, and then you have to calculate the similarity between each and every point in the higher dimensional space. Okay. Now, using kernels, how you are achieving that in the original space is something that you have to see. Now let's ignore what is this and what is this formula. This is one of the kernels that are available for us. We have few kernels that are available for us, and this is the form of one of the kernels. We call this as polynomial kernel anyways. We will come to that shortly, but this is one sort of kernel. Now, C is a parameter and D is a parameter. Okay. D is the polynomial degree and C is a constant. Now let's, for simplicity, let's make C as 0. Okay. I'm making C as 0. Now, x dot y whole square. Okay, this is the kernel comes down to. Now, when you do the dot product of x and y, 1 into 2 comma 2 into 3, so it became x 8, 8 square 64. Okay, now if you look at these two values, we haven't transformed the points. Technically, we haven't transformed the points. Okay, here when we are using kernel trick, we haven't transformed the points. What you have done, you have just calculated the dot product in the original space itself, but you were able to come with a value which is equal to the similarity calculation in the higher dimensional space. Understood? That is what kernel trick is. Kernels will not do any transformation of the points, but they will, using the kernel functions, the kernels will actually try to find out the similarity between the points in the original space, and using those similarities they will calculate the hyperplane that is separating both the points using the similarities. Okay, similar points stay together. Points that are similar have high kernel values. Okay, understand this. Now we calculated the kernel value of 2 points, and we found out that the similarity score in the higher dimensional space is can be achieved by using just the dot product in the original space by using the kernel functions. That is what it comes down to. So kernel functions simplified the process of transforming the points to higher dimensions. We don't really need to transform the points to higher dimensions. We can just do the dot product in the original dimensions only by using the kernel trick, by using the kernels. So similar points stays together. Points that are similar and have high kernel values and are placed close together in the transform space, reinforcing their belonging to the same side of the boundary. Points from different classes are less similar, and those mapped further apart in the transform space, helping the SVM to find the margins or boundaries that separates them. So how is similarity calculation actually working is, it's as simple as this. So what it is trying to do is, if you just carefully observe this slide, you will get most of the stuff that you want to understand. So what kernels are trying to do is, kernels will calculate the similarity between the points in the original space. Using those similarities, they mimic the similarities in the higher dimensions. Using those similarity scores, they will try to find out the boundaries. What it says again, when 2 points are more similar, they will be close to each other, and if 2 points are not similar, they will be far away from each other. Okay, so that actually tells you that using those similarity scores in the transformed spaces, they will find out that these two belongs to similar class and these two belongs to similar class, and they'll try to find out the line between them. Okay, that's how it actually works. If you look at this particular animation, you will understand. So in original dimensions, it is calculating the similarities between different points, which is equal to calculating the similarities in the higher dimension spaces. Okay, so it is actually calculating the similarities in the original dimension spaces, but kernel trick is transforming them to higher dimensional spaces. Technically, to keep it simple, we are not actually going to higher dimensions, but we are mimicking the similarity calculation in higher dimensions by using the kernel trick. This trick, calculating the higher dimensional relationship without actually transforming the data to higher dimensions, is called as kernel trick. Again, look at this. So you are doing the similarity calculations in the one dimensions, which is equal to similarity calculations in the original dimensions. In the original dimensions, you are directly calculating the dot product. In the original dimensions, you are using kernel trick, but in the transformed space, you are doing the actual dot product. So that kernel trick is actually doing that transformer dot product. Okay. So if it is a three-dimensional space, you do the similarity calculation between each pair of observations in three-dimensional space, and you find out the hyperplane. That is how kernels will actually achieve that trick without actually transforming the data points to higher dimensions. Okay. So this is a simple thing. Now tomorrow we will understand what are different kernels are there, what is a polynomial kernel, how it is actually doing the transformation and finding that variable, and the other one is radio basis kernel. These are two important kernels that we will study tomorrow. I think that's all for today.